No, that's on my list, and I'm also like, yeah, it's one of my.
Yes.
So yeah, it's nice on the clock. It's nice to talk and I'll get that. Yeah, and I'll continue this. Yeah. All around the business. You're standing right next to it. Yeah. 1.52 guys. 1.52. So that all of the crosses are satellites right now.
Wow.
I work. Yes. So he also needs to frequency. Yes, absolutely. Yeah. So Monday and Tuesday are we created 5 to 8 models. So yeah, it's that's how you do it. And you see the movie.
Yeah, sorry.
Yeah. Yeah. So and the only way that we're working on it, we don't have to.
Yeah, yeah. I have to run. You will be here.
Yeah.
You will.
Testing. Would it be okay for me to try sharing my slides?
Yes, you may. You may go for it.
Thank you.
So I just saw your share, but it didn't complete the share yet. So I didn't see what you were sharing exactly.
All right, let me try again. There. And this is going to work better.
Okay, got it.
Is that coming through?
Yes.
Okay, excellent. Thank you.
Thank you.
Oh, by the way, I'm presenting in another session just before my talk in this session, so I'm going to have to exit and come back later.
Nice.
So my other talk is at from 10:50 to 11. So I will rejoin shortly after 11.
Okay, no problem.
Thank you.
Gonna die, they're gonna stand by your grave. Give up that illusion, give up the addiction. You need a second opinion.
Want to speak?
No, I just want to. So welcome back to the second day of the future of radio astronomy in a crowded spectrum. So we are missing the first talk, so we will jump directly to Benjamin Hugo, and he will give a talk about RFA mitigation software and limitations. So please grab the floor. Oh, I should say, my name is Mikael Lindqvist. I'm from Onsala Space Observatory in Sweden.
Okay, let me just get to the first slide here. Back does not seem to be working now. Sorry, my back button doesn't seem to be working. Oh, there you go. All right, thank you so much. Okay, thank you so much for the organizing committee to having me here today. So I'm going to be speaking about the software aspect to RFI mitigation. I'm on the FM5 working group as part of panel working on the white chapter or white book chapter on specifically on software. So I must point out that this is not just my work, I'm presenting work and also literature survey on behalf of this wonderful group of people here. So Jonathan, Chris, Harry, who was here yesterday, and Ravashi. So I'm going to be presenting both work from the NRO, on the SKO side, and from Soraya. And then also a bit of a literature overview. All right, so let's get just into this. So just to recap, if you ask a radio astronomer what RFI is, it's sometimes a bit different to what an ITU member might say it's RFI. For radio astronomer, anything that interferes with their particular science goal is interference. So it can be either naturally occurring interference, so for instance, solar interference, so also a form of interference, or it can be man-made, of course. So the man-made ones, interference, we can classify as broadband interference and narrowband interference. So narrowband, you have primarily ground-based interference, so air and satellite transmitters. The broadband interference, you have things like spark plugs and like sparking from electrical overhead electrical lines, et cetera, natural ones will be like lightning strikes, actually also is interference. From the IATU's perspective, and for this purpose of this talk, I'm going to be focusing more on the man-made source of interference. The IATU formally defines interference to be any source that has a power flux density of more than 10% of the primary user within the electromagnetic spectrum. So it defines primary users and secondary users, and radio astronomy only is a primary user, for instance, at near the 21 centimeter line. So it allocates bands to radio astronomy, for instance, that one. However, it doesn't, in the other bands which are allocated to the telecommunications industry or navigation, etc., those are, only in those aspects, radio astronomy is a secondary user. So there is no protection for us. We may listen in at our own peril, but there's no protection. Even within our allocated bands, contamination is tolerated to some small margin. So this is something to keep in mind. So designing transmitters is a hard job, so there is some tolerance here as well. All right, so just to highlight here the EM spectrum, you would have seen this yesterday if you were here. This bits here in this dark purple is radio astronomy. The rest of the band is other things. So there's aircraft transponders and satellite, navigation satellite, et cetera, all in these other bands. So this is the UHF band from 300 upwards, and then the super high frequency band from 3 gigahertz upwards, is according to our regulatory authority here in South Africa. So radio astronomy is a primary user in very small parts of the band really overall. So just to give you an overall sense of where we are. All right. So mitigation is really critical for our modern instrumentation. Why do we design instrumentation to have ultra wide bands, you may ask? Because we're letting up a whole slew of problems to deal with. Well, both in the continuum and line sciences, it makes sense to have very wide bandwidth instrumentation. For the continuum sciences, if you want to go very deeply, observe very deeply, then you need wide bands. What happened to the screen? RFI, indeed. Okay, so I'll just continue on while they're sorting out. So for continuum emission, you need wideband to actually get to your sensitivity. And if you want to study like spectral indices, as Kenda pointed out yesterday, you need good sensitivity in various subbands in that wide bandwidth to be able to do that kind of modeling. For context, so we're looking at observations of like, if you want to put it into dB watts per this dB watt scale, then we're trying to aim at minus 290 to minus 310 dB watts, right? If you look at like millijansky to microjansky population. For context, GNS satellites operate, for at least for Baidu, in excess of minus 190 dB watts. So it is 10 orders of magnitude above like even the moderate to faint population of sources that we are looking at, right? So it is very bright. For spectral lines, the spectral lines may either be redshifted to bands that are not allocated to radio astronomy as primary users. So this is why you'd need a wide bandwidth instrument in end. So the goal of mitigation and management is to preserve as much of this wide band as possible and as feasible, even in the secondary bands. All right, so RFI mitigation management entails both regulatory side, as we've seen, and also on the technical side. So on the regulatory side, you have management through dedicated quiet zones, as we have in South Africa, in the Karoo, where permits need to be issued. If you want to have a transmitter, then you need to get a permit, and that permit depends on how close you are to the core of the SKA, or Meerkat as it currently stands, and or the arms, right? Similar for the Green Bank Observatory, I think that's probably the most well-known, and there's also now one in Western Australia that you've seen yesterday. All right, and it entails also then, of course, measuring and management and like enforcement of that zone. That's key part. So we have stations and even mobile stations throughout like our site in the Karoo. All right. So why do we need to protect the cores of these large interferometers so carefully? You may ask, well, a radio interferometer, unlike a single dish, don't only measure power. Like you don't only steer the single dish, or a single dish you steer to get a power reading. For interferometer, it gives you a power reading and where that signal is coming from, right? So you get a power and a phase here. So, and that's done per spacing, right? So it depends on the length of the spacing and depends on where that source is relative to the center of your field of view. Now, if you have a short spacing, then if you average that signal, it's a complex number, you retain the amplitude. If you have if you do an average on a longer spacing for an off-axis source, then that amplitude diminishes. So for a transmitter, so I've shown for a relatively short baseline here on the left-hand side, so 300-meter baseline, you can see that most of the RFI isn't washed out through this process. For a long spacing, some of that amplitude diminishes, at least for the sources that are non-stationary. For sources that are stationary relative to your telescope, that's a zero fringe rate, so it's not affected by, well, it's not mitigated in this natural sense of using interferometers. All right, so that's when you don't have a saturation event. You could also have a saturation. So here I show a saturation event courtesy of Ian Hayward, for a GNSS satellite that's going straight over it through the beam of the telescope. And you can see that over here, over here where the satellite passes through the beam, there is saturation through the entire band. So you have to throw away that entire section of time, right? You can't recover there. All right, so what does this look like in image space? Well, I would argue that in image space, it's even for radio radio telescopes, it's even worse than an optical case. Where in optical case, you just have a stripe of pixels that get wiped out by something that's very reflective. Well, in radio, you have like all these, because we have an unfilled aperture, so our instrument response is not quite as defined as a large optical telescope. You have the side lobes of a source traveling through the image here. So you can see this GPS satellite starts over here, then it travels up and through the image. So over here, it's almost at the center of the field of view. So it's already within the primary beam. And you can see that it saturates the signal as it moves straight through the beam. So to remove this before and after saturation is probably possible. You can essentially peel it off, but it's very computationally expensive to do that because you have to do it at a high cadence, and your modeling needs to be immaculate to do it at high dynamic range. So it is a very hard task to do, and it's probably not worth the effort. All right, so in terms of software mitigation, we need to do mitigation from the front of the telescope all the way to post-processing where the user receives their data, right? So I would say that you can't just do it at the end. You have to do RFI through management to the end user product. Now, at the detection level and at the correlation level, you can implement a bit of basic thresholding and filtering. Now, as I've taken this picture from the source over here, so I've indicated sources over here if any of you want to do some further reading. So at the front end, you can design your receivers to be robust, so they don't get saturated in hardware. So you add more bits in your digitizer, etc. So was explained yesterday. And you can do some spectral filtering there. And then if you can have before you correlate, you can do thresholding. If you have RFI that's localized, then that is quite necessary to do before you correlate. And other techniques also exist. So if you have a reference signal, you can try and subtract that signal out of your measured signal. So your I try to think of it this way. So if your excision cadence or the cadence that you can do your RFI excision at increases the further out up the stack you go, the sensitivity of your excision, so you can catch the bright stuff, very, very bright stuff that's interfering over here. The low level RFI you can only catch in your integrated product. So, right, so you need RFI mitigation all the way through the stack. Okay. All right, so Arvashi did a bit of a study for the NGVLA at the NRAO. So I'm just going to show just a brief summary of that study. So they considered a few cases here. So they modeled the biggest contaminants here. So cell phone, satellite, mobiles from vehicle radars, I should say. All of these contaminating sources. And so they considered a few cases here. So there are like RFI that is short duration and like quite persistent, but like high duty cycles. Those are usually commercial and like military communication protocols. And so post-correlation algorithms, if you do it at a high enough cadence, can get rid of that quite well. Then there's also the short duration infrequent RFI. So things like airplanes with their transponders flying past, right? So those things may not be visible to all of your antennas if they're very far separated at least. So yeah, so those are best suited for real-time excision. Then the persistent RFI So those are like cell phones and like GPS satellites, for instance, persistent RFI. Those, it also depends on where, if they can be seen by the entire telescope, but those are like, it depends on their locality and their, but they're at least subject to decorrelation on long spacings. All right, so this is just a bit of a plot to show you the RFI that you can exercise, the percentages if you do it on a pre-correlation or post-correlation level over here. So if you go from 1 to 100 gigahertz, your excision is typically between 26 and 34%. If you do it, and this is so this after your archival rate integration. If you do it pre that rate integration rate, then you can do a bit better, right? So the online pre-correlation RFI mitigation they found to be only of benefit on like very pulsed emission. Okay, so the imaging science cases. So for the continuum side, at least, typically RFI excision is done via some form of adaptive thresholding on various window sizes. So Andre's some thresholding algorithm in combination with implementing high-pass filters to remove radio backgrounds. For instance, if you're on the galactic plane, there's very bright radio sources around you. So this is very sensitive on how well you do that background subtraction, essentially. It's implemented through a high-pass filter, so it's a bit of a knob-turning exercise depending on where you are observing. So this is implemented online and offline for Soreo, and it works quite well for narrowband and like persistent RFI. Then you can also get like for broadband RFI, of course, if you have a lot of broadband RFI, then you can't really flag all of that out and you lose a lot of your data. So if you, I'll try to just wrap up quickly. If you have, you can also subtract these sources out if you have good enough modeling, but it's very computationally expensive. For H1 cosmology, this is perhaps the worst case scenario where we're trying to detect signals that are like very structurally compact in the frequency space. So this is along the line of sight in frequency. And over here on the x-axis, it's the spatial scales is, well, it's an image plane. So over here we have the foregrounds, and so these are spectrally smooth, and so we can't observe here, but we could potentially detect the cosmic level H1 in this window. So anything that's spectrally compact is a big problem here, and determining that level of where we can possibly get good detections is a bit of it's very challenging if you have RFI. So you need to be able to remove your RFI to like very high spectral dynamic range of like 5 orders of magnitude, so up to like millijansky level, which is a very big challenge. So this is, you have to do, you just can't do per baseline basis. You leave a lot of RFI that way. You need to do it like on the integrated products. So for filter bank, there's filter bank. So as I said, interferometers measures amplitude and phase on a per spacing level. So if you sum all of that up essentially coherently, then you get only a single like time frequency observation towards a specific point on the sky. You can do it coherently or incoherently to broaden that a bit, but essentially that's used to do the high time cadence, so like up to like sub-millisecond level time cadence products, which you need for pulsar observations and FRB observations. And the FRB observations are very challenging because you want to trigger like a visibility buffering based on detection. So you need to be able to excise your RFI really well. This can be done with like DM filtering, so looking whether that signal has gone through the interstellar medium or not. Yeah, so I should say that machine learning shows quite good promise here to mitigate this. Just future work is, I believe this where we're heading is, we need to coexist with industry. So the NRAO, they work with SpaceX to try and mitigate, at least for the Green Bank and the VLA observatories, that's so they see that for by SpaceX steering their beams away from the Green Bank, it's good enough. They also did experiments where SpaceX turned off their beam when they passed the pointing where Green Bank was pointing. So, it is possible to work with industry, and I think this is perhaps going to save us at least some bandwidth in the future. Thank you very much.
Thank you very much. And give you a pin from crowd. And as yesterday, you will get a pin if you ask a question. So are there any questions to this talk?
Yeah, sorry. In SARAR terms, we talk about the pipeline or science data processor. Is that where the RFI factor is?
Yes, so there's a median absolute deviation basic filtering applied in the ingest process where the data rates are really high. Those samples get integrated into archival sort of integration ranges, so like your 8-second samples that you see from your measurement set when you analyze your data. So we have some filtering there, and then also this gets the highest level of RFI, and then on the visibilities themselves in the online pipeline, those are flagged with a some thresholding based algorithm as well. So, and then it can be calibrated at least. So,
any further questions? If not, let's thank Benjamin again.
thank you.
So the next talk will be given by Sri Krishna Sekar, and he will talk about grid flag, RFI flagging in the UV domain.
Morning, everyone. I'm Krishna. I'm an assistant scientist at the NRAO. Today, I'm going to talk to you about some of the work that I've been doing along with some of my collaborators to work on this flagging algorithm that works on the UV plane. Let's hope this works. Okay. I'll go through some necessary background. Most people here are familiar with it, but just in case, talk about all that stuff. I'll explain the actual algorithm and then show you some results. So actually, Ben Stock, thanks, Ben, set this up really well. RFI is anything that we don't want in the data effectively. It's kind of the most generic way that you can define it. And the point I want to make here is that it can and will occur in every combination of time and frequency characteristics. We don't really get a choice. It just happens. And so because of that, it can be quite challenging to figure out how to deal with it. And kind of the way that I like to think about it, and as Ben pointed out as well, is that you have to stage it, like different kinds of things are good to detect different kinds of RFI. What I'm going to talk about here is all the way downstream, post-processing, post-correlation, post-averaging, all of that. But there's many things you can do on the way to kind of save yourself the trouble at the end of the road. We're all familiar with this. I just want to point out that in a radio interferometer, what we are measuring is the Fourier transform of the sky, and every visibility that we measure is a single Fourier component. A V of UV is a single Fourier component, which will be relevant in just a minute. Further than that, the UV plane defines the effective aperture that we're using. So the more filled it is, the better, the better our sensitivity, the better our PSFs. And what we don't want to do is, if we've got RFI in the data, what we don't want to do is blow holes in the UV plane. You've got a bad baseline, you throw away the whole baseline, suddenly your UV plane has a big hole in it that didn't exist before. And because the UV plane is measuring Fourier components, what that ends up meaning is that we lose sensitivity to spatial scales at those particular spatial frequencies. And if we're imaging kind of big, fluffy, diffuse things, that low surface brightness objects, they tend to live in the shortest UV spacings, which is also where most of our RFI lives. And so if we start to throw away UV coverage, then imaging these kinds of objects is particularly difficult because they both kind of occupy the same part of UV space. So grid flag is an algorithm I developed using my PhD. It's actually very straightforward. I could, if it was just this, I could have done this talk in about 30 seconds. The kind of insight into how this works is that for instruments that have a limited field of view, the visibility cell size, while we're making the image, you have to grid the visibilities, and the cell size in the gridded visibility plane is determined by your field of view. And once you have made that choice, you have no loss of information while gridding. So what that means is, let me try to go back. So you've got different baselines that cover the same part of the UV space. And the point is that they don't all do that at the same time. They do that at different times. And different baselines are kind of sensitive to different RFI environments. The RFI might be switched on for one baseline, switched off for the other. And so what ends up happening is that if you've got multiple baselines putting in visibilities into the same part of the UV grid, they're all looking at the same Fourier component, but they're sampling different RFI environments, which means that hopefully only a fraction of the points that fall in that particular UV cell are affected by RFI, and you can actually go there and find it and throw that away. So back to RFI for a second. Ben made this point again. Thank you. In some senses, bright RFI is easy, right? It's a kind of a flippant thing to say, but if this is a Meerkat L-band spectrum, everything is in red is fairly persistent. It occurs for most data sets most of the time. And you can kind of see it's bright and booming, and you can throw it away. What is really difficult is faint RFI, right? RFI that's kind of on the level of your visibilities or slightly lower than your visibilities even. And why that's a problem is that RFI is not stochastic, so you don't get the advantage of time averaging. So your noise doesn't go down with time. So you could observe 100 hours, but your sensitivity is determined by the level of the faint RFI. And in fact, you might only notice that there's RFI after you integrate 20 or 30 hours. You might not be able to see it in a single observation. But the nice part about something like grid flag is that you're not looking at a single baseline. You're looking at all of the baselines that dump the values into a single UV cell. And what you can do is fairly trivially is stack 100 hours onto a single UV plane. And cool. All, your RFI tends to pop, right? So if you look at this plot, you can kind of see that this is the U and V, and grayscale is amplitude, so you can kind of see where the RFI is. And if I blink between before and after applying grid flag, you can kind of see that the grayscale gets quieter overall. Most points, the amplitude kind of drops, but the UV coverage is largely preserved, right? We're blowing some holes in it, unavoidable, but it's largely preserved. So if you look at the statistics, even when we're flagging about 15% of the points, we're only throwing away about 3% of UV bins, which means we're trying to preserve UV coverage as much as we can. The algorithm is fairly straightforward. We just calculate the median within each UV cell, determine a threshold, and then flag it in the raw data. Right? Very straightforward, not complicated. here are some results. The blue is the original data, and the orange is the flag data. This is RMS as a function of distance in the away from the phase center. Similarly, just a histogram of points in the image, you can see that the histogram kind of shifts leftwards, which is what we want. This is all from GMRT 150 megahertz data, which is, a great test data set if you want to look at RFI. And here's an example in the image plane. You can see that all these bright ripples that go through the image kind of tend to go away. Before I run out of time, I want to talk about some work I did with a summer student, Jonathan Hanna, who I was told this morning is no longer in Oakton, but he's in University of Illinois, Urbana-Champaign. He implemented grid flag, a version of grid flag in the Libra project's gridder. I'll be done in a minute. The Libra project, if you want to know more about it, I have a poster, FM7 this afternoon. You can come ask me then. But we implemented it in the gridder, so we implemented flagging during imaging, so you kind of get flagging almost for free. Not quite, but it's fairly cheap. You run flagging every major cycle, so the added computational cost is not particularly high. He implemented it in the COCOS framework, which is what the HPG gridder is implemented in. It's a framework that you can compile down to CPUs and GPUs, the same code base. So we've got this working on the GPU. And you can check out the main Libra repo here and his version of the HPG gridder on his repository. It's still kind of in progress. We've got the prototype working, there's all of that, but we're hoping that we can have a gridder that kind of turns on flagging if you wanted to while you make the image. We're also working on implementing the grid flag algorithm in the Viper framework, which is something that NREO is working on in collaboration with, some parts in collaboration with SKAO and Sarao and things like that. But yeah, I believe that's my talk. Thank you.
Okay, thank you very much. Sure. So do we have any questions? Yes, we have.
Thank you. John McKean, I'm Surrey on University of Pretoria. As you go deeper and deeper, these things are going to become an issue, but then how do you deal with low-level source variability, low-level calibration errors? When do you start to get that mix? That's the first question. I just need one pin. But and the other thing is are you using any type of sky model when you're doing the thresholding, or are you just looking at just the raw RMS statistics?
So probably the easiest way to get this done is to do it when you've created the residual visibilities. So you image and then subtract out everything that you've imaged. But like you said, that still leaves out low-level sources in the visibilities. But the point is we're looking at statistics per UV cell, and all of the low-level sources are going to kind of cluster together with a similar mean and standard deviation, but your RFI is going to sit somewhere else. So even if you have some amount of low-level sources in there, it's not going to make a huge amount of difference. Similarly, with low-level calibration errors, it gets a little trickier. And so you might end up flagging some real data, maybe if you stack 50 or 80 hours. But by and large, I don't expect it to be a huge problem.
Have you tested it with simulations, like really to look at this? What is the cutoff?
We haven't yet, but that is on the list.
You only get one. Right. I mean,
just a quick question. So do you propagate, you mentioned that you do this during the imaging mapping from visible to image. Do you propagate those grid flags back into the measurement set for calibration purposes afterwards?
So that's something we're looking into. The cheapest way is to not do that and just reject points as you're accumulating the grid for imaging. Which is why we started looking at it. But then we realized we've already got this grid with the threshold, so we may as well go back and flag the raw data. So that's something that we're very much looking into.
One. All
I have like
okay.
open.
Okay, the final question here.
Thanks, that's really interesting stuff. So I'm curious if there's a limit on the short end of things. So for example, if you have a very short observation of a few minute snapshot.
Yep.
In particular, if you're only doing, a very quick snapshot of a calibrator, how well does this do for your calibration scans?
Not well. I mean, it's not going to be more or less advantageous than looking at it per baseline, basically. The real power is when you can start stacking.
Really get deep into the.
Yep.
Great, thanks.
All right, let's thank the speaker again. Next talk will be given by Ramaila. Right. And he will talk about RF Finder.
Hi, everyone. My name is Athanasius Ramaila. And today, my colleague Filippo and I will be giving you a presentation about RF Finder, which is radio frequency interference, data evaluation and reduction. So this is a tool that I'll get into it. So the previous speakers have already mentioned what RFI is and how it hinders us to performing science. And one of the most challenging is when you find it in your data and it mimics the science that you're trying to do. If you're interested, you can see the reference that I put there where they try to show some of the difficulties and challenges that I experienced when dealing with RFI. And this is prominently in the low frequencies, or this mainly affects us in the low frequencies, especially when you're studying a spectral line or 21 centimeter lines. And I should mention that also there's been research focused on algorithms, as the previous speakers also pointed out. So I'll just leave the reference there. So speaking of new generation telescopes like the Meerkat and the upcoming next generation telescopes such as the SKA and NGVLA, all of these instruments promise an unprecedented sensitivity. So, and we are experiencing the same issue, which is RFI. Here I show a plot of a typical 8-hour observation from the Meerkat, and you can see most of the interferences coming from the satellites. Coming from mostly satellites. And now when it comes to reducing the data, so now we're dealing with the data offline. So we already have our data with interference. So where RF Finder comes in is that when you receive the data as an astronomer, mostly you have to go through a process of data reduction, which is the process of calibrating your data and reducing the RFI. So here I show a snapshot of a pipeline that we implemented. Also, you can check out the poster. So we use multiple tools. As I mentioned, there's a list of tools that are developed for flagging RFI. Also, there are a list of tools which are used for inspecting the data. RFI mostly focuses on RFI evaluation. And also another advantage is that you can use it even to pre-inspect the data, not only after you flagged. And I should mention also that all these tools are available within the pipeline that I demonstrated there. So you don't necessarily need to use it on its own, but you can use it within the pipeline. So as I already mentioned, so it's a Python tool, easily installable from PyP, and you can generate plots from movies which shows spectral windows and time chunks of your data, mainly on two premises. So we have two modes, where the first one focuses on investigating the presence of RFI. The second one, we study the statistics of the flagged data. So here's a sample plot which shows a baseline against frequency, and this uses the the first method that I demonstrated. So basically you're doing a threshold clipping. So you look at your data and see which windows are much cleaner, and you use those to estimate the noise for thresholding in the data. And for this typical observation, you can see we selected a threshold of 5, and it shows the percentage of the data that lies within that. And this is before even we do any flagging. You can see at the edges, you can still see bend roll-offs having a low noise, but we know we're gonna flag those later on. And then the next set of plots, this is when you, also I should take this opportunity also to acknowledge Professor Tom Osterlo for assisting in this particular part of the project. And then there's another set of plots. So this here, I demonstrate the flagged statistics. You can already see at the edges, I removed the pen roll-offs, but since we run an automated strategy here, it also removes some of the flags, and then it shows you the percentages. The 1D plot of the same plot is given below. And even with the previous one, you can get the 1D plot, which also shows you the noise, not only the statistics of the data that is above a certain threshold, but you can get the noise predictions as well. And then here it shows you the statistics of the flagged data. And you can also select the range of baseline ranges to see how much of your data is affected for each baseline. And as I already mentioned, you can select this in different chunks, so you can study different windows as well in time, and you can study different windows in time. And here also it gives you opportunity to look at each baseline. And these statistics can be computed from various correlations. In this particular case, we focus on linear correlations, which is XX and YY, and some Stokes parameters. In this particular case, I plotted the Q, which is also a form of a combination of the two correlations. As I already mentioned here, I applied a strategy which automatically flags the data. And then after that, I'll want to reinspect and see how much of the data has been flagged. And also, as I say, you can use this as a pre-inspection tool. And this can guide you also in setting the thresholds of the tools that you use for flagging. Another interesting plot is the altitude and azimuth. So as I already mentioned, you can chunk your problem into different sizes in terms of frequency and time. So this just shows you the transition of the source being observed at different frequency chunks. And also it shows you the statistics of the flagged data. And you can follow which frequency bands are affected at which altitude. And then another set of plots, this gives you basic summary statistic plots. You can get scans. So in your whole observation, there's different parameters that you'd be interested in. This would include scans. You want to see how much of the scans has been flagged, and then you want to look at antenna statistics, frequency. You look at the whole bandwidth, and then you can also plot the correlation statistics. And also, beside the plottings, if you just run the tool, you get a summary of the observation, similar as what Catalyst Ops, if you're familiar with that, it just gives you the information about your observation. And then in conclusion, as I mentioned, RFI is a tool which is available on GitHub and can be easily installed from PyP. Its two main function is to investigate the presence of RFI, and also you can use it post flagging to assess the flag data statistics, and it can be easily installable. But as I said, if you're doing data reduction, mostly you wouldn't even need to install it because you can use it within a workflow environment or within a pipeline. And the nice thing is that it generates a report, which is HTML, and it has all the plots in there, and it's easily shareable. You can open it in any browser. Yes, that's the end of the talk.
Thank you very much. So do we have a question? Yeah.
Thank you. Interesting talk. I just want to ask, how do you optimize the value of the threshold when you do the clipping?
So currently, this is an option that is given to the user. So we use a Sigma clipping algorithm, but basically you just specify any number as the user, and then we get a cleaner window, and then we get the noise statistics in that and apply the thresholding based on that.
Okay, thanks.
Do we have a final question? Yep.
Interesting talk, thanks. Can be imported in CASA? Do you have a module that can be imported directly in CASA?
So as I mentioned, CASA, so I was showing that we do something that is much similar to what CASA is CASA doing at that particular instance, but this is different from CASA. So mostly it's a command line tool which can be used on its own, but I mentioned that you can install it within other pipeline environments. So I know CASA, they have a CASA pipeline. So if it allows using external tools, this is a Python command line tool that can be interoperable with any pipeline or workflow environment.
Any final question? No, let's thank the speaker again. So the next talk will be an online talk by Jean-Luc Margot. Let's see if we can have him upload.
Yes, can you hear me?
Yeah, we can see you.
Do you have my slides?
Yeah.
All right, thank you. Hello, everyone. I'm pleased to talk to you today about the impact of radio frequency interference on radio SETI. Now, the reason we conduct searches for radio technosignatures is to expand the search for life in the universe from primitive to complex life and from the solar neighborhood to the entire galaxy. And there are a few advantages to radio SETI compared to biosignature searches. The first one is cost. It's about 3 orders of magnitude lower. The second one is search volume. There's at least a 6 order of magnitude larger search volume in radio SETI searches compared to biosignature searches. A third advantage has to do with the certainty of interpretation. If we detect a narrow band extraterrestrial signal, it will be compelling evidence of another form of life with no false positive. And finally, there's the potential for information content if a transmission is encoded with information. Now, at UCLA, we're conducting this SETI search in a tightly integrated mode with an annual SETI course that we teach to about 20 undergraduate students and a few graduate students each year. The students design an observing sequence, use the Green Bank telescope, download terabytes of data, and then they write code to analyze the data, and they publish the results as co-authors on our paper. So we're searching for narrowband radio signals with the GBT. And by narrowband, I mean 3 hertz, much, much lower than anything that any astrophysical source can generate at L-band. And we're searching for these signatures between 1 and 2 gigahertz in L-band. And with this particular telescope setup, we can detect an Arecibo planetary radar out to about 415 light years. And if we make the reasonable assumption that an advanced civilization can muster, let's say, 60 times the power of the Arecibo radar, then we can detect them all the way to a kiloparsec. And if we go further and assume they can muster maybe 3,000 times Arecibo, then we can detect them all the way to the galactic center. Now, I'll be showing you dynamic spectra in this talk where time increases down on the vertical axis and frequency increases to the right on the horizontal axis. And I want to point out an important characteristic of our search is that we're preserving the full time and frequency resolution of the data. So we have a frequency resolution of 3 hertz and a time resolution of about 0.3 seconds. Our colleagues at Breakthrough Listen, in part to accommodate a large data rate, do an incoherent averaging by a factor of 51 in the time dimension. But we'll see that that results in a very diminished sensitivity at non-zero drift rates. Speaking of drift rates, we anticipate a line of sight acceleration between the emitter and the receiver. And in our pipeline, we search a range of drift rates between 0 and approximately 9 hertz per second. And it turns out that this range is sufficient to capture most line of sight accelerations due to the orbits of confirmed exoplanets. And if we make a small assumption about the distance between the planet and its star, it actually captures 100% of these orbital line of sight accelerations. It also captures 100% of reasonable spin line of sight accelerations. To identify RFI, the first filter that we implement is to detect non-zero Doppler drift rate. So anything that has a 0 Doppler drift rate does not have a line of sight acceleration with respect to the telescope and therefore is radio frequency interference. So we require a non-zero Doppler drift rate for a technosignature. And our second filter is based on an on-off-on sequence. And in this filter, we require the signal to be present in both scans of the source, but it cannot be present in the off scan. And anything that is present and that is detected in the off scan is automatically labeled as RFI. And these two filters in conjunction are actually remarkably good at identifying RFI. Here's a distribution of our signals on a 4-year survey of a test sample of exoplanetary systems. And we detected in the survey 41 million signals. 99.4% of those were automatically detected as radio frequency interference by these two filters. Now, that still leaves a couple of 100,000 signals, but it turns out most of these, this is the same plot on a log scale, most of these overlap with radio frequency interference. And it is difficult to do SETI in those bands. It's much easier to do SETI in bands that do not have prominent RFI. To characterize how the RFI impacts our ability to detect signals, we conducted a careful signal injection and recovery analysis in which we injected 10,000 artificial signals with a uniform distribution in frequency and frequency drift rate. And then we ran these data through a pipeline to verify which ones were detected and which ones were not. And this plot shows you the injected signals in brown and the recovered signals in orange. And again, you can see that we're doing fairly well with the worst performance clearly associated with these RFI bands where fewer of the injected signals are recovered. Overall, we're getting a 94% recovery. Outside of these RFI regions, we do much better, 98 to 99%. Now, we conducted the same analysis with a breakthrough-like process in which we do the time average by a factor of 51 and then run turbo SETI. And as you can see, the sensitivity to high drift rate signals, non-zero drift rate signals, is considerably diminished with only 6% of the signals recovered. We are interested in excising automatically prominent sources of interference, and here are some examples of RFI that we detect frequently. And Megan Lee, in her PhD work, is designing a machine learning tool to automatically excise this interference, and we want to make this tool available to the community. To develop the training set for this machine learning tool, we established a citizen science collaboration called Are We Alone in the Universe, in which volunteers are presented with some of our dynamic spectra, and then they're walked through a classification tree, and they can assign classes of RFI to these spectra. And this forms the basis of the label training set that Megan is using to create this machine learning tool. Currently based on, this is very preliminary, we have a ResNet 34 implementation, which gives us a fairly high confidence score in identifying RFI classes. Here are the F1 scores for recovery of these classes. Some of these are reasonably good. For some of the other ones, we're still refining the algorithms and the training set to improve the performance. So to conclude, we've observed 55,000 planetary systems to date. We've detected 82 million candidate signals, no ET and no need for reobservation so far. RFI remains the biggest challenge to radio SETI, and we can use injection and recovery analyses to determine the impact of RFI on our search. And we're currently implementing a machine learning-based RFI excision tool with a label training set provided by a citizen science collaboration. And if you want to learn more, go to seti.ucla.edu. Thank you for your attention.
Thank you very much. Do we have any questions?
Yeah, IAU GA from Max Planck Institute here. Thanks a lot for this nice introduction and talk. Is there an estimate of how or whether you have how much signal is lost by RFI in your searches? So any estimate of, well, what kind of chances to detect SETI?
Right. So that
drops
signal injection and recovery analysis tells us that outside these dense RFI regions, we can recover 98 or 99% of the injected signals. But when we're inside those dense RFI regions, it drops, the performance drops, and the overall rate is 94%. So that gives you a sense of the impact. The problem with the RFI is that it creates signals that intersect the signals of interest, and when there are those intersections in time, frequency, space, that makes it much harder to have a reliable detection.
Do we have another question?
Thank you very much for your talk. I have a quick question regarding what characteristics of the signal you're looking for once you remove all the RFI from your search? Like what I guess defines your definition of extraterrestrial life from these radio signals you're trying to search for?
Thank you. Yeah, so a narrowband signal. So let's say, for instance, 3 Hertz wide signal that nature cannot generate, that is emitted from beyond the solar system, for us would be pretty compelling evidence that there's some other engineer out there that is creating and transmitting these signals. And so far, none of these narrowband signals have been attributable to an extraterrestrial source. Every single one of them has been attributed to RFI.
All right, thank you.
Okay, if there are no more questions, let's thank the speaker again.
Thank you.
Now we come back to South Africa and America, and we're going to learn more about how to use machine learning by Harold Koo. Please go ahead.
Excuse me, is there no newer slide? Yes, thank you. All right, thank you for waiting. So, hello everyone. I'm Hano Gu, a postdoc at the University of the Western Cape, Cape Town in South Africa. So I'm working with my supervisors, Michelle Lohner and Mario Santos. So thank you very much for giving me a chance to introduce my ongoing research work in the title of application of, sorry. Sorry. So in the title of application of anomaly detection to meerkat radio data using machine learning techniques. So here's a brief introduction about my project. First, the meerkat radio data is a precursor of a mid-frequency square kilometer array, in short, SK mid. It's a promising source of large sets of radio data. And if we can find anomalous signal, it will bring us to new areas of astronomical research. For example, anomalous signal, there's an example anomalous signal, including gamma ray bursts, technosignatures, and so on. And to perform anomaly detection to such an enormous data, it requires an automated methods. And applying machine learning techniques will be more efficient and reliable way to detect anomalous astrophysical signal. Okay, so before I move on to the, before I discuss how the analysis goes, I need to explain time frequency dynamic spectra first. This is spectra of the radio data, which with x-axis with time and the y-axis with frequency. It's reverse frequency, and it's useful to visualize real-time radio events with varying intensity. So you can see different colors here, which indicates varying intensity. And this image, and so the machine learning methods for feature extraction and anomaly detection will be applied on these images. And I also need to explain the Sparkis X data. This is a simulated radio data based on the real radio data from the Sparkis Muriang radio telescope. It consists of known signals, including noises and pulses, and likely anomalies, including negative and dispersion measure pulses, splines, and steganographic images. So this simulated data is useful to test methods before applying the methods to the Meerkat data. Since Meerkat data is much larger than is very enormously large, and better to apply and test this method using this much smaller data. Okay. And yeah, after these explanations, I'm going to explain which steps I'm going to take for the analysis. Step 1 is pre-training CNN, which means perform typical CNN except the final classification layer for pre-training. Or other supervised or self-supervised machine learning methods can also be used. Step 2 is feature extraction, which means extract known and anomalous features using pre-trained CNN. And it can be visualized. The extracted features can be visualized by using UMAP. The last step is anomaly detection, which means detect anomalous signals using unsupervised machine learning methods. And I'm going to explain them one by one. So I already mentioned a convolutional neural network. So I just called this CNN. So I'll explain how to use CNN for feature extraction. So unsupervised learning methods generally can only work on lower dimensional representation of images. In other words, features. And many supervised or self-supervised machine learning methods can be applied for extracting these features. That should be done first to perform unsupervised anomaly detection using unsupervised machine learning. And convolutional neural network is one of them. And it's mainly used as a classifier. But CNN can also be trained as a feature extractor by ignoring the final classification. So if you see here, see this picture, this figure, you can see the process of CNN. It starts from input image and performs multiple convolution and then reaches to the flattened layer. From here to here is feature extraction. It's for feature extraction. Next to that, the fully connected layers are for classification. And the final result, probabilistic distribution. So from here, from the flattened layer to the last output, they are all for classification. But if we exclude this, if we perform CNN from input to only flattened layer, this becomes feature extractor. So this is what I mentioned as CNN for feature extraction. And the extracted feature using this CNN as a feature extractor can be visualized using uniform manifold approximation and projection. In short, UMAP. And it generates approximated lower dimensional representation of the data. And it visualizes extracted features in arbitrary units. You can see in this figure, there are x-axis and y-axis, but there's no units because they are arbitrary units. So you can see the extracted features like this and this one, and you can see so many points. And these points represents the dynamic spectrum. So each point it represents one dynamic spectrum. And yeah, this is a way to visualize the features. So among these features, for example, we can find outlier, like in the red box. It can be artifact or the real anomaly. Unfortunately, in this example figure, this one is just artifact. But and removing artifact during the feature extraction is very important to find real anomaly. And next, I'll explain about the next step, which the last step, which is anomaly detection. That among many unsupervised machine learning methods, I'm considering two methods. One is isolation forest, which repeatedly and randomly divides data into two and identify the data isolated in fewer steps. Another one is local outlier factor, which measures local deviation with respect to its neighbors and identify the data with lower density. So you can see my circles, and their radius corresponds to local deviation. And if necessary, other unsupervised machine learning techniques can also be considered. And this anomaly detection has a possibility to be applied for removing anomalous RFI. So radio frequency difference, I guess you know the definition. So this is the primary continent we're hunting for genuine anomalies. So it's harmful for so many research subjects. And unsupervised learning could be useful to detect and remove anomalous RFI. So typical RFIs can be removed using the previous method, but anomalous RFI, I think I would say the unsupervised machine learning using unsupervised machine learning for anomaly detection could be useful. And then here's a summary. So I'm pre-training CNN for feature extraction and perform it. And the next step is detect anomalies using unsupervised learning method, including IF and LOF. And it could also be applied for detecting and removing anomalous RFI. And I'm going to apply the tested anomaly detection methods on the much larger Meerkat radio data. And further discussion can be done at the question and comments, and also at the e-posters area. You can see the schedules here, and if you want, if you need more information, you can scan here and get the posters and slides. Thank you so much.
Thank you very much. Very interesting. Are there any questions?
Yes, please.
There we go.
Hello, my name is Boris Sorkin. I'm from Square Kilometer Array Observatory. First of all, thank you very much. It's a very interesting, very good work. If I may, just a small question. As far as I know, convolution networks are really strict in terms of what data you input in them. It has to be in consistent format. So I think probably maybe as a first step, you have to be in line with the equipment that you have. So you have a specific time resolution and frequency resolution, but different facilities might have different equipment, which might provide you a little bit different shape of data that you can feed in the model. So I just wanted to ask if your model tries to take that into account somehow, or this model has to be trained for each facility independently, or there is a possibility to use pre-trained data at one observatory and just pass it to another one. Thank you.
Okay, and thank you for the question. And I think that should be done for each independently for each data. So I mentioned that. Okay. So I mentioned that. Sorry. So I mentioned the pre-training CNN here. So during when I pre-train the CNN and use that pre-trained CNN for feature extraction. Before I do the feature extraction, during this pre-training stage, I think what you mentioned could be done. So I think, and that should be done here, and then after that we can move on. Yeah.
All right, let's thank the speaker again.
Thank you.
The next speaker is Chris Finlay, who's just here. Okay, thank you. Okay. And we talk about Tabascal. So please go ahead.
Good morning. Yes, my name is Chris Finlay. I'm a PhD student at the University of Geneva. And I'll be talking to you about Tabascal, which stands for Trajectory-Based RFI Subtraction and Calibration. Ooh. Is that me? Okay, there we go. So just a little bit of motivation. I mean, fortunately, there's been a great introduction by many people on RFI and some of the problems. But for those that are maybe interested in the money side of it a little bit more, about 30% of the Meerkat L-band is contaminated with RFI, and a lot of it is reasonably predictable. So many, as you can see here, and laser right there. Cool. This is all satellites over here. Then we've got an aircraft, and then we've got some stationary GSM towers. So reasonably predictable in the sense that we're probably going to know where it is, at least after the fact. Maybe not exactly what the signal is, but we know where they're also occurring in the frequency range. And if we think about the cost of developing Meerkat up until getting L-band going, it was about $330 million. And if you're throwing away 30% of that data, you can imagine $100 million just being burnt up. I do have an asterisk here because we've now got a few extra bands, so that cost is going down. As you know, UHF has got a lot less RFI than L-band. So Tabasco. So the goals of Tabasco are really to try and replace RFI flagging with RFI subtraction, right? So when we're subtracting the RFI out of the visibilities, then we're looking to recover the astronomical visibilities. So just the signal of interest, right? And what we want to do with it is to try and fit it into the current data reduction workflow, right? So you've got 1 GC and 2 GC. So you're looking at a calibrator source, and then you're trying to characterize your instrument, as in calculate the antenna gains. And then 2 GC is where you're doing calibration and imaging at the same time. So you're sort of calibrating on the target with some prior information from your calibration observation. And the ideas that we've got to try and enable this are that we've got these RFI trajectories, and we can use these to help us estimate the visibility contribution from these sources of RFI. Right, so for like satellites, we can calculate what track they're moving on. Planes, we know where they're going. A cell phone tower, we know where it's sitting, right? And we can also estimate antenna gains using some prior information, right? So whether that's information from clean channels or using this specific method for sort of the calibration observation, and then using that prior information for your target observation that has been contaminated as well. And also to further constrain the problem, we know that the astronomical visibilities themselves are going to exhibit some sort of smoothness, you know, in time in comparison to the RFI signal. So the RFI signal generally vary quite a bit as it's maybe moving through the primary beam of the telescope, but the astronomical signals will vary quite smoothly, and that'll be baseline dependent, right? Varies faster on a longer baseline compared to a shorter baseline. So towards this end, we've got some data simulations, and we're simulating satellite and ground-based RFI sources. We do sort of like a correlator averaging to simulate that fringe loss that you have with RFI specifically. And we can include time and direction dependent gains, and this is all implemented in JAX and DASC, so you can run it on a GPU and scale it up. So there's the GitHub link for that, and in future, the Tabasco algorithm will also be on there, but for now it's just the simulations. So just a quick note on the simulations. It pretty much gets done almost exactly the same as for astronomical signals. We've got a brightness matrix that gets put in, and we just change this slightly for an RFI source. We've got these geometric delay terms, which for RFI, then we include the fact that we've got curved wavefronts, so knowing the exact positions of antennas and the satellite, for example. We include a primary beam and like a bandpass, direction independent gains. And more specifically is sort of this correlated term. So we need to simulate at a very high time rate and then average that down so that we can get an appropriate simulation. And that gives us all out our visibility, right? So here we've got a forward model that's suitable for RFI sources and for our astronomical sources. And then we just combine this all into a big joint model where we're trying to estimate all the parameters. So for example, we've got our RFI trajectory parameters, the RFI signal at each antenna, and then the antenna gains. And this all gets put into the big model to get us out our visibilities, and that goes into a likelihood. Right? And all of these terms here are actually priors that we put on these in order to constrain the problem a bit more. And so therefore we have a big Bayesian model, and we can actually get reliable uncertainty estimates out of that. So Tabasco 1 is sort of applied to a calibration observation. And we can see there that we are able to recover our antenna gains. Oh, that's the wrong button, this one, which is over here. We've got our gain amplitudes and our gain phases. And depending on what you assume, you can actually increase how good your gain solutions are for your phases, essentially calibrating on your RFI. And that's what we've got on the top plot here is the RFI in blue and the astronomical signal in red. So Tabascal 2 is now moving into target observations. So we're now using our estimates from Tabascal 1, so 1 GC, right, just in the presence of RFI. And we have now got prior estimates for our gains. And we're now going to enforce smoothness in the visibilities through what's called a Gaussian process. So that allows us to set a prior on the covariance of these parameters that we're estimating. So the smoothness of the signal over time. Oh, wrong button again. And I can't get back. There we go. So we've got a shorter baseline that varies smoothly and a longer baseline that varies more quickly. I'll skip over this, but basically we're able to get uncertainty estimates in a scalable way using this specific method, and because of our implementation of using JAX and being able to do auto differentiation. But it's a very neat way in order to actually get uncertainty estimates out at the end. So in conclusion, Tabascal 2 is able to subtract RFI and actually recover the astronomical visibilities. And at the expense of more computation, we can deal with stronger sources of RFI or multiple RFI sources. And we can also get uncertainty estimates with an accuracy speed trade-off using the method I didn't get to explain, but please come talk to me if you're interested. And as far as ongoing work, we're just testing the limits of Tabascal, and we've got, it's called an EDA 2 station. So we've got some data there that we're having a go with. Thank you.
Thank you very much. So it looks like we don't have to tell our funding agencies that we will waste $100 million.
Well,
right,
then I maybe get some more money.
Thanks, Federico De Bruno from SKO. Thanks, Chris. Great job. Do you have any estimate of what would be the computational power you would need to implement this on not a few GNSS satellites, but 5,000 low Earth orbit satellites which move much faster?
Yeah, so currently for a single frequency channel, for a single satellite, it's 1 GPU will get it done in real time. So quite a bit, but we are working on improving that, and some funding is in the works for that.
Okay, final question.
Thank you very much again, Boris from Square Kilometer. Also, echoing what Federico said, it's very interesting work. If I may, I'm sorry if it's a slightly dumb question about the testing limits of this approach. What makes me curious is just for sure, I guess, if the receiver goes into saturation, there is no possibility to recover the data no more.
Yeah.
But is it possible to go a little bit further into non-linear domain? Do you try to take that into account, or do you work only in linear domain? Thank you.
Yeah, thank you for the question. Yeah, very good one, and often comes up for sure. Yeah, so currently we just assuming linearity, but it's not inconceivable to try and model the non-linearity of the receivers and include that. But for now, we're just working linearly.
All right, let's thank the speaker again. And now we move into the VLBI world, and Jung will give a talk about geodetic VLBI.
Astronomy and geodetic as well. Hello, my name is Taehyun Chung from Korea Astronomy and Space Science Institute, and I'm going to talk about some impact. Yes, okay. But impact on efforts on our efforts on spectrum management and then some activities from Korea. Okay. Yeah. Okay. Yeah, okay, thank you. And okay. Okay. Yes, as you know, VOVI is measuring the time delay from the source using the from antenna to the front and back end system, and then actually RFI and then other things can be affected on our data set, of course. And then also there are lots of signal chains which can be also affected by the RFI. And currently, I mean, the astronomical point of view, also geodetic point of view, the broadband system and broadband spectral measurement becomes more, I mean, general and also popular. As you can see here, we have the EAVN, East Asian VAVN network collaboration toward M87 Black Hole Jet, including the EHT. And then you can see lots of, this one is a quite high frequency, but also there are astronomical point of view, this kind of, why this window is always up here. Anyway, we measure this delay, and then the RFI can be affected, the measurement of this delay. And in case of the geodetic VOVI, and you can see this geodetic VOVI is linking to ICRF and ITRF, and then so there are lots of delay parameters that can be affected by the that can be coming from the other natures or source, and then also geometry of the telescope. And VOVI is very unique space geodesy technique that provide ICRF, ITRF, and the first set of Earth orientation parameters. So nowadays, global VOVI network, as you can see here, VAVA, and then EVN, also East Asian VOVI network, and LVA, that covers from quite wide range of frequency from 100 megahertz up to 100 gigahertz. And then also it was well known that GMV, Global Millimeter VOVI Array, and then also the EHT, also having quite high frequency, like 86 up to 350. And also, in case of IBS service, I mean, International VOVI service for geodesy and astrometry, and there are many of stations that are working at 2.3 and 8.4 gigahertz in the legacy band, and then now becomes more popular Vigo system that from 2 to 14 gigahertz. So this Vigo system is really growing at the moment, and then 11 stations in operation already, and then more to come. And this system is actually cover from 2 to 14 gigahertz, quite large bandwidth, measuring the precise group delay measurement with compared to the legacy SX band system. So this kind of technical advancement, and then also the is actually produce a better result, but sometimes we also have suffered from some limitation of the systematics. However, in case of the receiver development, as you can see, the VOVA receivers are cover quite wide frequency range, and then also here KBN Korean VOVA network has simultaneous four different frequency band observing capability by implementing this complicated quasi-optical system so that we can observe from 18 gigahertz up to 150 gigahertz at the same time simultaneously. Also, Brigos receivers developed by Yebes Observatory, and you can see the 2 to 14 broadband receivers, and then also brand receivers, digital kind of digital VOVI receivers is covered from 1.5 to 15 gigahertz. It's a direct sampling. Actually, it means that there is no down conversion. So it's pretty much better, I mean, for the RFI protections from the data. And then I haven't included, but recently, I mean, last year, JPL Caltech published their multi-octet receivers that covers from 8 to 40 gigahertz. And then this kind of receiver development, and together with the broadband backend system like a DVB-C, and then also the octet, and that actually provide a better opportunity for astronomical and geodetic researches. Here I briefly, mention about introduce about our KBN, and the KBN is a 321-meter telescope, and then we recently last year we built a fourth telescope here in Pyeongchang in Korea. This is capable up to 230 gigahertz, and then the quite high frequency, which is relatively free from the RFI effect. But anyway, we also install, we have also C and X-band receivers and KBN Ulsan, and then also these receivers will be implemented all of the KBN in near future. So this is what we can get, with these receivers, and we can measure 4 different frequencies at the same time. So we can explore different wavelengths and then emitting material and regions for the research. KBN is quite actively collaborating with the others. It's likely basically the same as the VOVA plus P and KABA, Korea, KBN and Japanese beta array, and then also East Asian VOVA network, and LBA with Australia, EV and GMBA, EHT as well. So we actually carry out first the EHT campaign last April together with the KBN Yonsei telescope. And then this is actually current receiver, which will be completed development in a couple of months by the end of October. So this receiver actually covers, as you can see, from 6 gigahertz to 9, and then 28 to 34 CXK band receivers, and together with the CTR, 18 to 116 gigahertz, and then there is a SIX mixed receivers, and then 1 to 7 gigahertz up to 275 gigahertz. You can see here is this is actually CTR, which is installed at the KBN Pyeongchang new telescope. And then here we placed the rotating mirror. So this one is capable 5 this frequency observed at the same time, which covers from 18 gigahertz up to 275 gigahertz. And then we rotate this mirror to the other direction, 6, 9, and also the KA band capability together. So this kind of receivers and the new technology actually able to cover various picture of the astronomical and geodetic capability. As you can see, we also, KBN also measure this different major transition line of H2O, SIO at the same time. And then also there are lots of, the VOVI or the astronomical uses from 1 gigahertz to up to 30 gigahertz. And then recently, yes, ICRF sources, and you can see legacy SX, and then 24 gigahertz, even 32 gigahertz actually provide a very good, noise floor, which we go higher frequency, geodetic VOVI can be benefit from that. And you can see this is a recent our result. And then with the KBN, we firstly carried out 20 to 43, 86, and 120, 32 gigahertz simultaneous observation with the geodetic VOVI mode. And then this is the post-bit residual, which is submitted and then under review. And then you can see clear improvement when we apply the simultaneous calibration to our atmosphere. And then last April, we carried out first GMVA 86 gigahertz geodetic VOVI observation. So this kind of things can be done with the KBN and also other radio telescope so that we can see more, aspect in the future at higher frequency, which is relatively free from the RFI. And then lastly, there are quite, many radio telescope in Korea and working at different, sites, sometimes for the public. And then, this is a KBN Yonsei telescope, which is located at the center of the Seoul. And lots of RFI, but actually we clearly see that some RFI in case of the 6 gigahertz. And then so we actually matched up. We shielded this octave system coming from this digital converter. And then after that, we have some benefits. Yeah, well, actually, we also in the geodetic VOV station as one of the IBS station, we actually are developing the band filter system for mitigate the RFI at S-band. And then there are also, we are ongoing effort on the preserve our, frequency for radio frequency for research. And we started forming a CASI working group. And then, so still high frequency, but still there are several things that we can coming from the other satellite like this. So in Korea, anyway, this is international, but domestically, we more, additional make a statement in the regulation for in Korea like this in order to preserve our activities. So this is a current our Korean frequency protection for our activities coming from here to there. Thank you.
Thank you very much. And it's also nice to see you that you are a part of the EHT family now. I could have one question before we break for lunch. There's one. All right, let's thank the speaker again. And let's thank all the speakers of this morning. And we will continue the discussion about the VLBI in this room at 1:30, including regulatory processes. So please be back at 1:30 in the same room. So thank you very much and have a nice lunch.
Yeah, measurements. This is the the wonderful way that you just nobody visit. Yeah, X-ray. And then essentially moving up to this selection, then you can and then yeah, actually so yeah, and then like the big guns, I think
let me try this. Hi. Just trying to contact or get into contact with Ashley. I'm online now.
Hi, Josh. Can you hear me?
Yeah, Vincenza, is everything I'm good to hear you. Everything
Thanks.
up and good?
Yes, it looks like I
Okay,
was
good.
just unsure about the level of the voice, if it is clear, but
No,
it's
I hear you loud and clear. And well, all the offline speakers, they have to start their presentations from their own by sharing, right? I just wanted
yes,
to highlight that.
yes. Thank you. Yes, I made. Hello, Tiziana. I made
Hi,
a check.
both of you. Ciao.
No, ciao. Okay. Let me-
Yeah.
So here I am too. So I made a try previously, and it seemed that it was working well.
I also tried this after I saw Vincenza's presentation and it shows up. So I think it should be okay. It's a very simple presentation. So we are ready, Josh.
We are ready. Yes.
Wonderful.
How
I'm
many
looking
people are
forward.
there in the audience? Because it seems very crowded from the
Yeah,
images.
I'm excited. It's about 60 persons at least. It was really crowded. Let me see. 1, 2, 3, 4, 5, 6, 7, 8. 8 times 4, 32. Could be 90, about 90 persons here in the audience. So we have really had a good, very good resonance here.
Okay,
Let me
very
see.
great. Congratulations. There are also like on average 15, 20 people online. So altogether, this brings up to more than 100 people. That's very nice.
I'm really glad about it. We need additional. Sorry.
Okay.
Okay, so we'll
Thank
talk.
you very much.
I am already here. So as soon as the conference starts, I'm ready.
Wonderful. Great.
Okay,
Thank you
me
very
too.
much.
See you later.
Thank you.
Goodbye. See you.
Ciao. See you later, Vincenza.
I remember. Yeah, yeah. Yeah, you can unscrew the bottom leads, put it from the inside. Like. It's up to you. Session that after this one.
I think I'm in the other one, yeah.
And I'm in this one or there? Oh, okay. Well.
So we don't know if that's going because So first we have two talks about PLBI. And then Ashley is supposed to come.
Yeah.
We don't know. I don't know. But,
Okay.
So you could be up or
Okay.
But I guess you can talk forever. So
I can surely do. So I really need. So yeah, that's why.
So could we be seated, please? So my name is Mikkel Lindqvist. I'm from Onsala Space Observatory in Sweden. So welcome back to this discussion about RFI and what we can do about that. And now we're going to have two talks about VLBI, and they will be online. So the first talk is by Tiziana Venturi. So we'll talk about, so could we have her talk uploaded, please? Or you will start, could you please start your talk, Tiziana? Yes, so we can see your presentation, Tiziana.
Okay.
And we can hear you.
Okay. Is it okay? Can I start?
Yes.
Okay. Okay. So thank you very much. I wish to thank the organizers for giving me a chance to present the work which is being done on the VLBI chapter of the white paper, which is in progress. This presentation is done on behalf of the full team of writers of this chapter, and in particular, I wish to acknowledge the contribution from the people listed here who provided me a lot of material. Okay, so just to give you a very quick outline, I will really provide a very, very quick introduction to VLBI and to the VLBI arrays. I selected a really small number of VLBI science topics, which I think should be brought to your attention because they are particularly challenged these days. I will very quickly present a couple of technological developments which are relevant in the framework of our discussion, and then I will conclude with some recommendations. So VLBI is basically the extension of interferometers with antennas which are separated by several hundred to thousands of kilometers from each other. This provides an angular resolution of the order of the milliarc second scale, but even less, even smaller if we consider high frequencies. So the frequency range the VLBI science is interested in is very broad. Actually, the VLBI arrays currently operating on Earth work in a frequency range which goes from 30 megahertz roughly to 230 gigahertz. So it's really a very broad range we are talking about. And between the array operating at lower frequencies, which is the International Low-Far Telescope, and the Event Horizon Telescope, which operates at 230 gigahertz, we have a broad range of arrays spread throughout the Earth, which operate in the range between 1 and 100 gigahertz. And the message I want to bring your attention to here is that the location of the different antennas in these VLBI arrays, which is, I mean, they are very different locations throughout the world, poses an additional problem to the RFI situation, because a VLBI array not only has to face global sources of interference, but local sources as well. And these local sources most of the time are very different from one station to the other. And this implies that, additional losses in the array can take place and additional reduced sensitivity. So because of its very high sensitivity, which is of the order of the microjansky per beam, and the very high angular resolution, VLBI is really a key technique for a broad range of scientific topics and novel scientific areas. And a few years back, the VLBI community produced a white paper focused on the scientific goals for VLBI in the current decade. And the collection of these science cases is really very broad, and it ranges from science in the local universe, as local as Earth, nearby stars, all the way up to cosmology. And the book, that white paper, also includes a technological roadmap, which basically highlights the needs and the requirements of the VLBI community in terms of developments which need to be in place in order to make sure that the scientific areas and the scientific goals can be achieved. That book really showed that VLBI is really making a lot of progress, and there is really a lot of enthusiasm both on the scientific side but also on the technological side. At the same time, this progress and this excitement has to deal with the increasingly worsening of the RFI situation in the bands which are which are interesting for radio astronomy. So here I just go through a few cases. The first one is the study of AGN at high redshift. And when I say high, I mean redshift above 6. The reason why this topic is really interesting is that very recently it has become clear that supermassive black holes, and when I say supermassive, I mean black holes with masses above of the order of 10 to the 9 solar masses at high redshifts, meaning redshifts beyond 6, are particularly interesting because their formation is a problem if we try to explain it in the current lambda CDM model, because of the Eddington limited accretion type of process, which would not allow enough time for them to grow such masses at those high redshifts. So one possible solution to overcome this problem is assuming that there are relativistic jets in them, because these relativistic jets would have large radiation efficiency and would then slower the growth time. So the only way to really test if the relativistic jets are in these objects is through VLBI observations, because we really need a millisecond angular scale resolution, possibly at gigahertz frequencies. So here in this bottom left panel, I show a number of, I show the case for one of these well-studied jetted high redshift AGNs. This has been observed in the panel which I show. It shows VLBA observation in L band, C band, and X band, each of them in rows. And the columns actually show the different bandwidths for the observation. The left column shows the image as it has been obtained using the full bandwidth of the observations, which is 512 megahertz. The central line, the central row shows the same image, but obtained only with 5 megahertz bandwidth, which is the protected bandwidth in L band. And finally, the right row column shows again an image with an even narrower bandwidth. So here it is very clear that when you reduce the bandwidth, the information on the jet disappears. Of course, we know that reducing the bandwidth also reduces the sensitivity of our observations, which of course means that we are losing the fainter features. So it's not a surprise, but this is really to show you that some science cannot do with the reduced sensitivity. And the other major point I want to make here is that X band does not include even a portion of the band protected for radio astronomy. And this is really an issue because AGN observations are best obtained and carried out at high frequencies. The second area I want to highlight is that of astrometry and geodesy. We have already heard about this by Tayo Jung this morning, and then Vincenza will tell more about this. Here I just want to bring your attention to the need both for astrometry and geodesy to move to higher frequencies. In the case of astrometry, which produces the International Celestial Reference Frame, the reference frame so far has been, which already includes more than 4,000 sources, has been historically performed in the SX band, But recently, it has become clear that it is important to move to observations at higher frequencies, partly because of the worsening of the RFI situation in S-band, but partly because if we want to improve the accuracy of the celestial reference frame, we need more compact sources which we observe at higher frequencies, at higher angular resolutions, and we need to reduce the core shift effect. And this shift would be towards X and K band observations. The terrestrial reference frame, as we have heard even this morning, is now, observations for the terrestrial reference frame are now moving towards the use of Vigos antennas, which are smaller and faster, and work with the broadband receivers in the 214 gigahertz band. And this provides a much better accuracy for the parameters. So both these techniques are moving and shifting to higher frequencies. And here I just want to show what this means in terms of challenges. In this left panel, I am showing the situation of interference in the 4 channels of the S-band of the dual SX receiver, which is much worse than what you see in the X-band. And here on the right, I show a panel which has been shown several times even yesterday. And here I highlight the situation of the allocation of the frequency allocation in the US in the frequency range which goes from 3 to 30 gigahertz, which is exactly what we are talking about for astrometry and geodesy. But for the whole radio astronomy, we are actually talking of a much broader window. And here you see how crowded the allocation is and how problematic this becomes. In terms of science, I really need to speak in favor of the methanol line. The methanol line, in particularly the one at 6.7 gigahertz, is vital for the study of high mass star formation. High mass stars are really a tiny fraction of all the stars, and losing the possibility of observing them would really imply a severe impact on our knowledge and on our progress on star formation and all the mechanisms at the basis of this. This line is particularly important on the one hand, because it is stronger than the other methanol lines at other frequencies, but also because it is a unique tracer of high mass star formation. It provides information only on high mass star formation, so it is really vital. It also has several other applications, and here I wanted to mention, for instance, the study of the galactic structure, which is carried out using methanol masers, and it is really a very successful project. So really there is a very strong scientific case to keep the methanol line free for radio astronomy. Finally, yesterday, Franz Kirsten provided an overview of the transient universe. Here, I just want to make a couple of points on the relevance of the transient universe for VLBI. We know that these phenomena have become very common now that the wide field instruments and also the capabilities of processing time domain observations has considerably increased. VLBI is really vital for transient phenomena because first of all, it allows the association with the optical counterpart, but beyond that, it also allows the location of this event within the host, which means it tells us which type of objects we are really dealing with. And studying thanks to multi-epoch observations with VLBI, we can also study the expansion of the emission for comparison with the models and the evolution of the structure with time. So the timing is really critical for this type of science. And if we come to severe RFI in one epoch, then a lot of unrecoverable information is missing. And if we have several RFIs in many stations of the array, then the sensitivity would really drop below the requirements. So that would really be a major loss. This is really my last slide. I still have a couple of slides, sorry. On the technological developments, as I mentioned, the community expressed the interest in going towards high frequency receivers and broadband receivers. And here I just wanted to show some cases. We have already heard about the 3-band receiver that the Korean collaborators have developed. And this really means observations between 22 and 100 gigahertz and above. So a broad fraction of the spectrum needs to be available for these observations. The brand receiver has been developed and for Bonn as a prototype for Bonn. It operates between 1.5 and 15 gigahertz, and already for Bonn, a number of hardware solution had to be placed in order to avoid RFI, severe RFI in this frequency range. Finally, I just wanted to mention the CX receiver developed by the collaborators in IEBES, operating between 4 and 9 gigahertz. And this plot here on the right shows the RFI situation in IEBES in 2022. So it tells you how much of the window is really affected. And the plot on the right shows the same situation in Medicina, where we are also thinking of putting this receiver. So much of the band is really affected. So just to conclude, VLBI reaches microjansky per beam sensitivities at very high angular resolutions. This is really important and key to address a number of open questions in several astrophysical areas. So the scientific future of VLBI is very bright and exciting, but at the same time, it has to face the challenges which are posed by the RFI situation locally and worldwide. We have already heard during this conference that mitigation measures are successfully taken both at hardware and software level to face the RFI situation, but this is not enough for us. And I also want to point out that the protection of the bands already allocated to radio astronomy is important, but it is also important to try to bring new portions of the electromagnetic spectrum to astronomy, to radio astronomy, to make sure that our science can progress. And I thank you very much for your attention.
Thank you very much, Tiziana. Do we have any questions from the audience here? Do we have a question online? All right, okay, let's take Tiziana again.
Thank you.
And the next and last VLBI talk for today will be by Geodetic VLBI, Vincenza Tornatore. So could you please share your screen, Tiziana, Vincenza?
Sorry, just one moment.
Yeah, no worries. Looks great. So please go ahead. It looks good, Vincenza.
Okay. Okay, here I am. I'm very sorry for the loss of a few minutes. And anyway, I want to thank all of you that are in this huge meeting. And what I want to talk today is about the activities that International VLBI Service for Astrometry and Geodesy, the IVS, and Committee on Radio Astronomy Frequency Interference, CRAF, has carried out in the last years to protect astrometric and geodetic VLBI observations from unwanted radio signals. Okay, this is just a slide that tries to summarize what are the main products from IVS. I will not explain too much because many things have already been told. I want to only underline that current international celestial reference frame is called ICRF3, and it's composed of 3 catalogs of radio source, extragalactic radio source coordinates, right ascension and declinations, that the current ITRF is called ITRF 2020, and it's materialized by not only by VLBI, but also combined with the GNSS, SLR, and DORIS, that are other space geodetic techniques. And of course, we have also the Earth orientation parameters that allow, in the same global solution, we can also determine the Earth orientation parameters that are 5 parameters and can allow us the rotation from international terrestrial reference frame and celestial reference frame. I want just to go in more detail or what means that we have such coordinates on the Earth or on the sky. These coordinates are very accurate, are very stable, and checked and estimated regularly. And so each catalog represents like a fiducial network of points. These points are very accurate, and we can determine position of other source, natural or artificial, both in the sky, so we have astrometry, or on the Earth, and we have geodesy. I just give a closer look to the network for the terrestrial reference frame. Here you see the starting network composed by legacy stations that observed at S and X bands. We have observations since 1979. At the moment, we have 40 stations, but they are of different size, from 6 meters to 100 meters, and many of them come from astronomy. The Vigos network is the result of some stringent requirements, including 1 millimeter accuracy and 0.1 millimeter ER stability, that were established by Global Geodetic Observatory System and was adopted by the IVS. So this system has also been described very well. I want to put attention on the receiver, the bandwidth. We have broadband receiver, and in particular, at the moment, the standard for Vigos is from 2 to 14 gigahertz dual polarizations. And so now I start this the core of this presentation that wants to underline why these reference frames and the Earth orientation parameters are so important for science and society. And on the left, we see that there are depicted smaller effect or movements that can change the shape of the Earth or movements of the Earth. And to determine this movement, these very, very little movements or change in the shape, we need stable and accurate global reference frames as ICRF3 and ITRF 2020 is. And also we need on Earth orientation parameters because they are also sensitive to geodynamic phenomena, to the Earth's interior. And so many applications are possible, many topics can be studied thanks to these reference frames. On the left, on the right side, there is a short list of some of these applications in the 3 fields, but I have also prepared at the end of presentation a list of references of these applications because it's very important to widespread the knowledge and the awareness of what we can do. Only because we have such reference frames. The problem is that the VGOS frequencies, the bands that for receive 4 bands of 1 gigahertz are very huge, and if we sum up the RAS spectra in this range, we arrive only to 250 megahertz. That's not so much. We have a worse situation even if we look to other passive service. So we started the action to ask for protection of VGOS frequencies. These are the steps necessary to reach this goal, and but it's a very long-term goal. In parallel, we have also people in the IBS that are making experiment and simulation to obtain a best set of frequencies for VGOS science. Other steps that we have carried out is to obtain support by international bodies as to enter in the European space law. We have the IAU resolution of 2021 that supports also the need to obtain a larger protection for VGOS bandwidth. And another resolution was approved in the 2023 by the IAU GA, that's a very huge union that is composed of 8 scientific international associations about Earth studies. All these resolutions are also sent to the directors of United Statistical Commission and Secretary General of ITO. Other strategies are at regional or national level, regulation at this level as the ECC decision 1704, and some also at national level. We can have some reference in the license that the nation gives to the operators. And here there are some restrictions for downlink and uplink signals from some satellites. Other possible actions that are also being mentioned several times are, of course, related to the site. First, register the VGOS antenna to the ITU register, so you are official Earth station and establish and maintain a radio quiet zone or become critical infrastructure, or this will give more protection to the site and continue with technical development and coordination. So this is the conclusion. Just I will not read these three parts. They are just I want to underline the fact that astrometric and geodetic VLBI needs also to become more visible and understandable to other field of science and also society. Therefore, outreach and training for next generation are welcome. And the outlook is to strengthen contact with bodies that can give strong political support for geodesies. So I thank you very much for your patience, and here is the list of reference. Thank you.
Okay, thank you very much. Is there a short question? If not, let's thank Vincenza again.
Okay.
And now we
Thank you.
will change chairperson and subject.
Right. So we will start the next session on regulatory processes. So the next speaker would be Ashley Vanderly. Yep. You ready to go? Okay. If you're ready, just unmute.
Yeah, can you hear me?
We hear you well.
Okay, fantastic. Thank you. Well, thank you so much. My name is Ashley Vanderlei. I wanted to just say thank you very much to the organizers. I know a lot of work went into this organization, and especially to Josh, lots of time. And it is very encouraging to see so many people online and so many people in the room. I wish I could be there. So many great talks. So I look forward to meeting many of you in person in the future. I wanted to just note, so I have worked in spectrum management for about 7 years. I work with the U.S. National Science Foundation and a growing team to try to help handle some of the spectrum management challenges. But I am a radio astronomer that focused on radio astronomy observations, especially of transient. So we've had a number of talks that have highlighted the importance of protection. But to me, one of the most kind of clear illustrations is if we're looking at making electromagnetic observations of transients. This is an example of the gravitational wave in 2017, and a fantastic detection was made with the Very Large Array. This is a paper by Greg Hallinan that was in Science, and this source was detected about 2 weeks after the gravitational wave event at 10 microjanskis at 3 gigahertz. And so one thing that is just very clear is that if you only had the primary radio astronomy band, which is less than 50 megahertz of bandwidth in that S band, it would have taken more than 185 hours of integration time to get to the sensitivity needed to make this detection. So this really illustrates the importance that we do need more access to the spectrum than the protected bands, as important as those protected bands are, because the source would have faded by then and we never would have been able to see it. So very, very important. So I'm here today presenting on behalf of a chapter on regulatory, on the international, domestic, and local level, and some hybrid measures. There's a couple of key questions that were provided by the organizers that I just wanted to share with everyone that I'm hoping to address briefly in the talk today and then more thoroughly in the chapter, including focusing on how is the protection of radio astronomy regulated, and more of this will also be discussed by Vadim at the end of this session. Examples of local radio astronomy protections, how do these work? Radio quiet zones, which ones exist, how well do they work? What are the shortcomings? How well are these solutions going to work in the future? And then what other measures are there beyond regulation to protect radio astronomy? I wanted to highlight, in this talk and also as we're thinking about the chapter, this is what I'm going to kind of walk through is the regulations on the international, national, or regional level, and then the local level. A little bit about the success and shortcomings, especially looking at the benefit, for example, of remote locations, but where that's starting to fall short, problems like unlicensed devices and keeping track of those. And of course, global systems like satellite systems are an increasing challenge. A summary of the radio quiet zones and also the fantastic news that we have an internationally recognized database of radio quiet zones now, so encouraging everyone to submit their information to that. And then future outlook, thinking about what needs to happen moving forward, especially with the direct-to-device and global systems, and then thinking about some solutions beyond regulation. There are a number of co-authors that are going to be working with me on this chapter, but I wanted to also invite anyone in the room, if you'd like to become a co-author or you have contributions, please reach out and would be happy to talk to you. I want to make sure we don't miss anything as we write up this chapter to kind of really help document what is possible in this area. So I think a lot of you know this, but I wanted to just cover at a high level. So regulations at the international level are made by the International Telecommunications Union. They have the international radio regulations, and there's a treaty every 4 years, which actually sets those allocations. Now, the important thing is that nations are still sovereign. So many nations take those international rules and they might modify a few for their own purposes, but there are many countries that actually just adopt the international radio regulations as they are. So it is important to know that there's that nuance that sometimes the international radio regulations apply, but sometimes there are modifications. In the United States, for example, we actually have in our Red Book, we have the list of the international allocations, and then you actually see how it's translated into US law. What's actually important here is that you're not supposed to cause any interference to neighbors. And so that's where things kind of start to come up if you make modifications within your country. As long as it doesn't, affect your neighbors, you're still operating within the terms of the radio regulations. This is a summary of some of the existing radio astronomy protections within the United States at a national level, and most of these have been sort of translated from international footnotes, but sometimes there's some additional US specific things. So for example, US 131 is a great example that helps to protect the 10.68 to 10.7 gigahertz primary radio astronomy band. And in the United States, our national rules give a few more details that says fixed satellite service operators must coordinate if they're operating in the adjacent band with this specific list of observatories. So it gives a little additional information and what that means in practice for the United States. But as you can see, for each of the sites that we have in the United States and the protections that exist, there still are a number of shortfalls. Mostly the shortfalls come into limited protection from airborne transmitters, especially the global systems like satellites. And then some systems have limited geographic protections because we haven't established a radio quiet zone. And I think the Very Large Array in New Mexico is a place where we really need one. And we've been working in the United States to try to make that happen. It's also worth noting that there are many radio telescopes across the world that are in completely unprotected sites. These might be telescopes at universities, for example, lots of smaller telescopes. And this is one thing we've been putting a lot of thought into, and I think it also highlights the importance of having the protected primary radio astronomy allocations, which hopefully will never change. So for example, neutral hydrogen, anyone should be able to make measurements anywhere. But for the more expensive and the larger investments, that's where I think we do need to start to focus on fewer geographic regions where we can get broader protections for our systems. Then there's also the local protections, and these can sometimes be the strongest. It could be at the state or the provincial or even the city level. In the United States, an example is within the National Radio Quiet Zone. We also have West Virginia has passed a rule with the Radio Astronomy Zoning Act that has a few additional details on top of the federal rules. Then even beyond that, some of the strongest protections can come locally, but you're kind of limited to the land that the observatory owns. In examples of the Green Bank Observatory, very, very tight restrictions, including on things like unlicensed devices and equipment like microwaves and all those kinds of things have to have tests. We've heard great examples also in South Africa. They have a fantastic database where they've measured the RF radiation from all kinds of devices. And so they have very strict rules locally. But that only helps for the things you can control locally. So that is where it's important to kind of think about broader protections as well. So a couple of the successes and shortcomings from the regulations that we have internationally, nationally, and locally. International, the protections when you do have a primary allocation can be very strong, especially if it's a 5.340 band where all emissions are prohibited. So this was good. And international allocations helped astronomers for many years because remote locations historically had been enough. For example, at the VLA above 10 gigahertz, it basically was completely clean for decades and decades. The shortcoming here is that as there's an increase in demand for spectrum, more and more bandwidth is also needed for science. Modifications to those international rules are very challenging. You only get a chance every 4 years, and there's lots of stakeholders. So that's a huge challenge. And that even for the protected bands, we still get radio frequency interference. And then it's also a huge challenge, the unintended emissions. And that's, becoming a bigger issue with these large global systems. National rules, a success, they can be stronger than the international rules, but the shortcoming is they could also be weaker. A nation could just decide that it's not important for them to follow. And so that's a place that it's important to have the advocacy within each country as well as at the international level. And then things like the global emissions from a global system like satellites, it's much more difficult, to handle with national rules. And then, as I mentioned, the local rules, very successful in mitigating many sources, especially the unintended emissions, but there's lots of shortcomings here, like unlicensed devices. One thing I wanted to highlight is we've seen in many cases, scientists and folks who even work at observatories, they want communications. And so this is really illustrated, for example, in the South Pole, where they need communication options, but they also need the dark sector to remain quiet. So there's some tension there, even with the community of scientists. And so this is something that can be a shortcoming with local rules. I wanted to mention just for protected bands, where you can have rules that protect you, but you still get a large amount of interference, which highlights, again, the need for maybe special geographic protections and other solutions outside of regulatory measures. So for bands, for example, like the 10.68 to 10.7 gigahertz band, there are rules that limit to 2% data loss, averaged over the sky. But what this means, this came from a report in Europe for Effelsberg. For this particular fixed satellite service, you can get peak losses up to 26 or 30% in the band where we actually observe the most, even though the average across the sky is less than 2%. And so even in the protected bands, I think we have challenges and we can't rest and say that we're actually finished. I wanted to show just some plots. So a credit to Frank Schinzel, who is now working with us at NSF. This just shows the change from 2014 to 2023 and the increase in discarded data due to various sources. And you'll see a big change in L-band. You also see a very big change in X-band, which is, I think, mostly due to the fixed satellite service, which is operating from 10.7 to 12.7, fractional loss of 6% going up to 16% over that time period. So this is definitely something that we really have to continue to work on and try to improve. Now I wanted to just touch quickly on radio quiet zones, with less than 2% of that spectrum being available below 5 gigahertz, and also these challenges where the protected bands still have a problem, having the time they need for science. This is where radio quiet zones are really, really important. So I would point you to this ITUR report, and big credit to Federico De Bruno, who I believe is in the audience, who spearheaded this update. This really gives a great overview, and this is kind of, I think, what we're going to be summarizing in the chapter of what are the characteristics of radio quiet zones. And the main takeaways, they're not really quiet, but they're quieter than other places. And the key is that they require coordination But the shortfall, as I mentioned, is that not always from global systems like satellite systems. The report includes all of these sites. So if you have a coordination zone around the telescope that's not listed in this report, please reach out. We'll make sure it's included in the chapter. And also maybe we can make an update to this report. Let me skip ahead with just a couple minutes left. I wanted to note within the US National Radio Quiet Zone, just again highlighting the
2
fact
minutes.
it's not completely quiet. There are over 1,300 cellular towers in the National Radio Quiet Zone. This is a plot with just one of the frequencies that shows where those towers are and all of the different places where we have towers. But this illustrates the challenge if we're going to have direct to cell from satellites. The fact that the satellites are going to be transmitting into a zone where we have carefully coordinated these 1,300 cellular towers over many decades. So it just highlights again, we really do have to think about ways to mitigate and think about the direct to cell challenge that's coming up. I wanted to highlight the international database that I mentioned that was approved at the International Telecommunications Union. So hopefully everyone will be submitting their information. And this is a great place so that commercial providers know where the important telescopes are, who to contact, and how to protect them. Future outlook, we all know that the demand is growing. There's lots of work to do, especially in the United States. We've seen a lot of pressure to repurpose bands, and I think this is being seen kind of across the globe. And so it's not just regulations, but there's also potential changes to the domestic rules. So I want to just skip to my final slide that is looking at what are some of the solutions beyond regulation. There's been so many amazing talks the past 2 days. These can include things like voluntary coordination, potential dynamic sharing. One thing that we really do want to work towards is best practices. So for example, to eliminate unintended emissions, for example, setting a best practice that satellites will perform measurements in an anechoic chamber over a very wide frequency band so they can find where those unintended emissions are before launch would be a great best practice. I'm also looking for technical engineering solutions similar to the talk given yesterday by Tony Beasley. I have the archive link to that paper where they've been working on bore site avoidance for satellites and observatories where they can share information. And then, of course, some fantastic software and post-processing, such as machine learning and AI. So all of this, I think it's great if we continue to work together. I think global coordination is going to be the most important thing that we can work together since there is so much work to do. So this is just kind of a high-level overview of what we hope to cover in this chapter and look forward to hearing from all of you. So thank you so much.
Thank you. Anyone have any question for Ashley? Online? Nope. Okay. All right. Thanks again. We'll have a next speaker, Boris Sorokin, to come up here.
Okay. So while we're waiting for slides, hello everyone. My name is Boris Sorokin. I'm from Square Kilometer Array Observatory, and would like to speak with you a little bit about our upcoming challenges for this current study cycle. First of all, I think many of you might know this. I see a lot of familiar faces in the room. However, for some others, might be useful to know that this button is not working. It might be useful to know that as well. Maybe I can ask for next slide, please. Yeah, thank you very much. Thanks to what Ashley mentioned previously, we have international treaty called Radio Regulations, which is reviewed approximately every 4 years, and that's you have these big circles. That's WRC, a very big conference where this document is getting reviewed. Between these conferences, so you see we have 2 big circles. In between, we also have a set of meetings, which is called a study cycle, where we deal with some new topics which were defined at the previous conference. So each conference makes a decision on something that was previously developed, and that will be the new reality of spectrum sharing for many countries in the upcoming time. And at the same time, there is another challenge that there is a preparation for the next conference where something else would be changed. So, oh, now it's working. Regarding the outcomes of the previous WRC, unfortunately, it's hard to make overview of everything. It's quite big and we don't have that much time. So I'm trying to focus on the most important ones. So the first outcome, which I'm going to talk about, is agenda item 1.2. It's extra frequencies for what we call in spectrum management IMT, and all of you know as mobile phones or cellular phones. At that conference, it was decided to identify extra frequency bands for usage of for these IMT purposes. So unfortunately, for those folks who look the universe in this frequency range, 6.425 to 7.125 gigahertz, you might expect that some base stations might emerge and cellular operations will start to slowly emerge across the world in this range as well. Luckily, thanks to hard work that Spectrum people did at the WRC, we got referenced the radio astronomy protection in in this small band, which is not even properly allocated to radio astronomy because it's only mentioned that administrations are urged to protect. There is no official recognition of use of that band. Nevertheless, we managed to get at least something there, which at least on that scale is quite successful. Another important topic is HIPS, which is high altitude platforms to be used as IMT base stations. So we are not only going to see base station emerging in 6 gigahertz, we're also going to see base stations to be installed on aircrafts that are going to fly approximately 18 to 15 kilometer height to provide service from above. You can also call them quasi-satellites because they are really high and they share the absolutely same problems as satellites. It's really hard to shield yourself from this source of interference. It's almost in the same direction as what we want to observe. So we were also quite successful at the WRC because when we were discussing frequencies around 700 megahertz to 900 megahertz, we managed to convince everyone to take into account the possibility of threat of second harmonics that might fall into officially recognized radio astronomy bands, especially the hydrogen 1.4 gigahertz band. And even though we were unable to directly mention it, we managed to get that these bands were identified to be only used by reception by these high platforms. So they're not going to emit in these bands. This is very good. It might be slightly different in different regions. ITU defines different parts of the world as different regions, but generally that's the rule, and that's really excellent, even though we didn't got the word harmonics being written directly. HIPS as evolution of hubs might create interference, but again, we might be lucky because hubs were with us since 1990s and there was no big deployment. So fingers crossed, maybe this thing will not be deployed as well. Okay, so the next important agenda item is agenda item 1.5, which it was dedicated to possible switch from broadcasting to IMT in 470 to 960 megahertz. There is an ongoing battle between broadcasting services like television and mobile networks, because now more and more people are using on-demand TV, so they don't rely less on broadband, and mobile operators see this as opportunity to get a little bit more spectrum for themselves. So unfortunately, even though radio astronomy is protected only in some small portion of this band. Luckily, we got some protection, but unfortunately, this band was upgraded to primary status in a set of countries. In other countries, it was on a secondary status, which I think some previous speakers already touched. So I'm not going to focus on that one. But unfortunately, the problem is that whenever mobile networks appear anywhere, they're really strong in favor. They tend to just throw out all other spectrum users out of this band. So unfortunately, in these low bands, maybe extra attention would be needed by observatories to see that this would not cause problems to them. So maybe there is need to pay more attention to local regulations or something like that. Okay, I'll try to speed up. So agenda item 1.10 is new non-safety aeronautical applications. Again, we were lucky. We managed to put some important text there to protect the. So another one, really good example is 1.13, upgrade of Scientific Space Research Service. Again, radio astronomy operations are protected by PFD limits. So these satellites, which will utilize this band, have to protect radio astronomy stations in adjacent band. New topics with most potential impact are, first of all, the global protection of selected bands and international recognition of radio quiet zones of SKO and ALMA. Only 2 sites were selected because, unfortunately, it's a really big topic for international community, so only 2 sites with big international participation were included. The other topic, I think others have touched it, it's supplemental satellite coverage for terrestrial mobile networks. And unfortunately, these possess a really big threat to us because they will be high powerful global systems that will create interference not only in band, but also via harmonics. Other topics also include space weather, lunar communications, another satellite topic. This cycle is really scientifically focused as well. So why this cycle is challenging? Many agenda items, they are relating to satellite activities, and we cannot shield ourselves from satellites because they are in the same direction as we are looking, the stars and satellites in the same direction. Now, nothing you can do. And if previously, you can see on the bottom on the left, if geostationary arc was just a portion of sky which you could ignore, unfortunately, with the modern development of non-geostationary satellites, it's not just one arc, it's the whole sky that is under the threat. So it's becoming a much bigger problem. So you can see, we cannot shield ourselves from sources like with mobile phones. I'll try to finish quickly. So we need to pay more attention to it. And one of the most important topics is consideration of harmonics emission. Unfortunately, currently, in the current regulation, harmonics emissions are not being taken into consideration. They're usually being hidden under spurious emission, and they are not taken into account because for normal communication systems, they are too weak. For radio astronomy, we are sensitive enough to see them, and this creates some problem because people in spectrum management tend not to really like this topic. You can see that in radio regulations, there is only one place where you can see harmonics. It's footnote 5.42, the only place in this giant document where you will see this. Also, what is important is that many radio astronomy stations are not officially registered in the ITU. For example, you can see in the middle of Africa, we all know that there is a radio astronomy observatory in Ghana. Unfortunately, it wasn't registered in the ITU. So whenever it comes to compatibility and sharing, it is considered that this station doesn't exist, which is a really big problem. So see this, please, as an encouragement that if your station is not yet registered, please try to do it. It is very important. Otherwise, satellite companies will not care about you. And the future outlook, what is really important is international cooperation. National administrations are usually contribution driven. So we need you. We need you to go to your national administrations and try to speak with them. Tell them that it is important, that you do important stuff. And astronomy is also a very important field because it's quite common that a scientist from one country is using an instrument from another country. So it's not only your national instruments that should be protected, it's global endeavor. They need to be protected globally because it's for international benefit. On the top, you see, for example, mobile operators and manufacturers, they already do this kind of union. And luckily right now in astronomy, we have that as well. And this is just an example of very good legal text that is to protect radio astronomy. No need to focus on that too much. It's very boring legal text, but that is exactly what we got thanks to big participation, first of all by CRAF, but also all other astronomers as well. So I'm deeply sorry for the overtime, and thank you very much for your attention.
Anyone have any question for Boris?
Boris, thank you for the presentation. I just want to ask, from the SKO side, do you work with SAREO in South Africa and the Australians in Australia to work with the local government, or do you directly work with the government? How do you do it?
Yeah, thank you very much. That's an excellent question because, yes, we do work with local authorities quite a lot. Actually, if I may, I would have a little bit courage and say that South Africa is a very good example. Actually, it's an excellent example of communication between radio astronomy's community and local authorities because we are able to speak with them to enhance some regulation, to comment on those regulations. And also South Africa supports us really strongly in the ITU. It's one of the biggest voices for radio astronomy currently. And so, yeah, we work quite closely with them, with SARAO and ICASA. And maybe you know, for example, Busang Sethole. So we are working really closely with him, and it's a very fruitful cooperation. Many of these results that you have seen, that I've presented, are all so much thanks to him. Of course, it's a global effort. It's not like one person can solve everything, but the South African role in all this is very big. So if I may, maybe just to extend that it's not only a good example, but it's maybe encouragement to all astronomers that we can do it. If we work together with local governments, exactly like we do with South Africa, we can achieve a lot of things. So, yeah, I hope that answers your question.
Okay, we should move on. Thank you, Boris. If any people have a question, we will have a discussion later. Thank you. We'll have the next speaker, Douglas Ball.
Thanks very much. It's a great pleasure to be here to talk about the Australian approach to managing the interaction between radio astronomers and all the other users of the spectrum. And I'm here representing CSIRO, the National Science Agency. We manage the radio quiet interactions and as I'll explain, the whole spectrum of the things that we're doing in Australia for radio astronomy, but also for some related activities. And I have to start with a great example of managing the spectrum and combining national opportunities for doing things well with the image from our galaxy, which combines Parkes data with the new ASCAP data and demonstrating how important it is to maintain the ability to do astronomy even in sites that are not as quiet as they once were. Now I have to learn how to use this device, I guess. Oops. That was too many. How can I go back? All right. So the Australia Telescope National Facility is our facility that operates the radio telescopes in Australia. So in the eastern coast, or near the eastern coast, the Parkes Telescope Murrayang and the Australia Telescope Compact Array. But in the west, the site where the SKA is being built in Yaramana Ilgiribundara, where MWA is operating and where ASCAP's operating. And we also manage for the NASA and for the European Space Agency, the deep space tracking stations in Australia. And so we've got a role in the spectrum coordination there. I wanted to start with a little bit of information, try to give the sense of Australia as a place and why we're doing radio astronomy in various places there. And this one's probably pretty obvious because we have a population that's a fraction of the US population, an enormous unpopulated area. And on this site, you can see our East Coast sites, which are developed sort of within a day's drive of Sydney, so practical to operate, but where the radio interference environment is obviously increasing. On the West Coast, you can see the site where we're now constructing SKA. And there's a population density as shown there. Of course, the population density in our site for SKA is only 2 millihumans per square kilometre. So it's very low indeed. There are around 100 people located in an area the size of the Netherlands. And for comparison, the most populated area of Sydney is around 20,000 people per square kilometre. So that's still much less than some other big cities in the world. Here's another perspective of the sparseness of Australia and the reason why we put the SKA site where it is. Those are the roads. In fact, most of the red roads and many of the green roads are still unpaved. So even though it kind of looks close to the West Coast and to Perth, it's actually a really remote place, but not so remote that we can't do business there. We can still drive there with only 3 hours down a dirt road. As a national observatory, we're running telescopes and instrumentation projects and sort of pursuing what I'm calling the whole hierarchy of controls that you want to, from sighting, whether it's terrain shielding or remote places, to regulation and acknowledging. Bolt sitting in the front row is our spectrum manager and co-author on this presentation. Government coordination, pretty successful working with the airspace regulator and with Defence on trying to do things in a compatible way. And we heard a number of talks about the progress around the world, also working with satellite operators. And that's one of our biggest challenges going forward. And we're working on that in Australia as well. Project coordination is perhaps less obvious. SKA is a major project under construction. ASCAP is observing. So simple arrangements we have that SKA constructs during fixed hours of every day. And that's the time when we might get more interference. And then we'll observe with ASCAP at other times. And where you locate your camps. So a bit more commuting trade-off, of course, having people have to commute a little longer to the construction site, but keeps them further away from telescopes that are being operated and commissioned. Choice of science projects. Technology I wanted to talk about. There are a few talks that Jane and Bolt presented earlier yesterday around some of these aspects. I'm not going to go into them, but design of the system, control of self-interference. And finally, perhaps last, is mitigation and subtraction and excision after even you've chosen which science projects to do when and where. For example, whether we're used to doing projects when the sun is not impacting us, or when the tropospheric at higher frequencies conditions are what you would observe in the millimeters when raining, and we're doing that as well, looking at things like when mobile telephone signals are ducted. So a case study is the Parkes Observatory. We've been operating this observatory since the 1950s, and the situation has changed very much, but it is in an area that has reasonable terrain shielding. There's a small hill between it and a town of tens of thousands of people. And we spend quite a lot of effort understanding local interferers and our own self-interference. And we've had good progress negotiating, coordinating with the telecommunications companies. We have 100,000 visitors a year, and they come to within 20 or 30 meters of the telescope. They bring their cars and they bring their phones. And so it's a combination of education and making sure that when they pay, we don't create RFI through the Wi-Fi of a payment system. And this is protected through a radio quiet a regulation, or the radio communications assignment licensing instructions that really give us the right to talk to the operators. So this isn't precluding operators from doing things near us, but it requires the operators to talk to us when they're doing something in various frequency ranges within a distance of 30 to 200 kilometers, depending on the frequency, and then the opportunity to propose the technical solutions. The radio quiet zone around the SKA site in Western Australia is a much stronger level of protection. And according to the frequency, we coordinate with operators out to 260 kilometers. So in the FM band, that's 260 kilometers at the highest frequencies, which are actually much higher than the frequencies that current telescopes are operating up to 100 kilometers. And so in the inner 75 kilometers, we don't have any transmitters at all. And the goal of the regulations here is to provide us a 50-kilometer radius where we don't have any impact from radio interference, or at least where it's below the level which should be interfering with our radio astronomy observations. And so this is both a method to communicate that interference and to calculate the level of signals, and also a coordination, a right to work with us on solving those problems. And so far, this has been very successful. So a few pictures now from that. I think I talked a little about the protections already. So let me move on just to a few results. Here's a nice plot of the 4G mobile phone systems, and the scale on that is pretty large. But that inner circle, I think, is 150-kilometer radius of the radio quiet zone, so that we can detect mobile telephone signals with our current instruments up to 800 kilometers away, depending on the ducting. But what you can see is we don't have any mobile telephone towers in the inner part of that radio quiet zone. That's a very important part of the protection. So coordinate with the new arrivals, but start somewhere where there aren't any. And finally, now just a comparison to give you a sense of the new site here made with the ASCAP telescope compared to Parkes. The plots on the right, satellites and aircraft on the left, you can see that mobile band between 700 and 1,000 megahertz. And here, a high frequency range that we're not currently observing in, up to 2.5 gigahertz, a very clean band. And this plot we saw yesterday is a great example of a very clean spectrum from 700 to 1,000 megahertz, enabling us to do really sensitive surveys of the universe that we couldn't do in other places. Thank you very much.
Thank you. Anyone have any question? Okay.
Did you end up having any traffic access restrictions for the site? I know like the Bellardi Road and caravanners or.
No, it's a public road. And as you know, but others may not, the traffic is still pretty low. So apart from our own traffic, dominated now by traffic around SK construction. So people who are just passing through, still only a few vehicles a day. The self-interference is the biggest issue on our site, I think.
Anyone have any question? I have one. So at the moment, do they have any restriction on the satellite passing over, say, ASCAP, like switching off, asking the
Yeah, so we're working with operators in the way that Tony described yesterday around NRAO. We're working on similar coordination arrangements. And Bolt is one who's working on that. I encourage you to talk to Bolt afterwards if you'd like to know a little more.
Okay, thank you. So we thank Douglas. And then we'll have a next speaker. Ask me.
Oh, good. That button?
Yep. You can press it.
Okay. Good afternoon, everybody. Actually, I don't know how to impress you because my presentation is already covered by previous speakers. So I hope you like my tie. Yeah. So my name is Vadim Nozdrin. I'm counselor of study group in ITU, in Radio Communication Bureau. And I have a big honor to be counselor of study group 7, space science, which in particular consists radio astronomy. So I will try to avoid duplication. Just for introduction, for those who has no idea what is ITU. So as you can see in structure of United Nations, we have a lot of different agencies and such as principal organs, and we have so-called specialized agencies. So specialized agencies, they have some connection with United Nations system. However, they have own budget, they have own Secretary General, and actually ITU itself was established much before UN itself. So ITU married with UN only in 1947, but it was established in 1865. So it's the first UN organization, and we are very big. We have huge membership, 193 states. So it's more than even UN itself, and we are open for participation of industry and telecom operators. We call them like sector members, and as well as we have contribution from different universities, about 100 academies which participate in activity of International Telecommunication Union. Headquarters is located in Geneva, and we have 12 regional offices as well. Our activity, as previous speakers already mentioned, is to establish radio regulations. I could say that radio regulations is like a Bible for any radio communication engineer. So it's established main principle of the use of spectrum on international basis, and actually it's one of few examples of international regulation which are mandatory and mandatory for all members of International Telecommunication Union, because after each conference, final acts has to be signed by each member states. And it's only World Radio Communication Conference has the right to update this radio regulation. And yes, last conference has been conducted in 2023, 4 weeks with about 4,000 delegates. It was quite heavy busy. But Boris already said something about results of WRC and future. I want just for those who doesn't know what is regulation, just to focus a little bit on the basic principles of radio regulation. So one of the main part of radio regulation is spectrum allocation table. You can ask how you can invent the rules to accommodate billions of radio systems in worldwide scale. We are very clever. We divide all radio communication system and so-called services. And we have now 36 services. So it's family of radio system with similar technical parameters. And based on the reference characteristic, we try to define the appropriate technical condition, how they can coexist. And for example, definition for radio astronomy service is you can find a radio regulation in provision 158. And just to show you what is the temperature of discussion in ITU, this definition was the result of very big fight, because telecommunication world didn't want to accept radio astronomy like radio communication service. So it's a big victory of people who defined interest of radio astronomy. And yes, as previous speaker said, basics in provision concerning radio astronomy is provision 5.149, which listed bands in which administration are urged to take practical steps to protect radio astronomy. Then very important for all passive services, not only for radio astronomy, it's footnote 5.340, in which list frequency band where all artificial emissions are prohibited. And then provision 5 to 8, it's apply some limits on active system like mobile satellite service, for example, to protect radio astronomy in adjacent bands. But I will not speak about WRC 2327. It's 23 was very heavy. 27 will be even more heavy. And I believe that Boris already spoke about this enough. So next activity, which we are doing actually in ITU, we have not only bureaucrat in ITU like me, but we have about 200 engineers. And in accordance with radio regulation, international protection of all radio system derived from the recording in International Master Frequency Register. And we actually maintain this huge database. So actually for satellite system, for example, you cannot launch any satellite and start operation without registration in this database. And it's explained in provision 8.3, and provision of radio regulation 11.12 says that radio astronomy station may be notified, might be included in MIFR, and provision 29.5 says that again radio astronomy station can be registered in MIFR, and they can get appropriate international protection. So actually it's normal procedure like for any kind of licensing activity. I could say that in order to be registered in MIFR, it's necessary just to send appropriate file, appropriate filing, appropriate form with appropriate technical parameters, and Radio Communication Bureau will proceed to make appropriate action, and appropriate radio astronomy station can be recorded. But I have to admit that it's concerned only specific location and frequency band which are allocated for radio astronomy. So if it's not, if you want to use frequency band which are not allocated to radio astronomy, from international point of view, you cannot get protection. And we publish, like Boris again mentioned, a list of radio astronomy stations which are registered. And new development in ITU and Radio Communication Bureau, we got instruction for after last Radio Communication Assembly that we have to establish new database which will include basic parameters of radio acquired zone for just like for information of administration that can be taken into account in order to protect radio acquired zone. And last activity of ITU, so as I have said already, that I'm counselor of study group, and we have 6 actually study groups. Study group 1 is responsible for general issue about spectrum use, and Boris mentions that we don't have study about out of band emission. Don't trust him. It's we have a number of recommendations which prescribe limits for out of band emission, but of course problem for the telecommunication world with out of band is completely different. So in many cases it's just ignoring. However, study group 1 is responsible for this issue. Study group 3 is responsible for development of propagation models, for analysis of electromagnetic compatibility. Study group 4, it's satellite services. Study group 5, terrestrial, and study group 7, science services. What is important to mention that besides producing technical analysis in preparation for WRC, ITU study groups, they produce recommendation reports and handbook. And they are not mandatory, not like radio regulation. However, recommendation and reports, they need the approval of all member states. So they give very good basis for technical discussion, because actually it's value which are included in recommendation reports, they are agreed by all ITU membership. And I put on the slide just basic recommendation concerning radio astronomy. So we have very good handbook, old one, but very good, which actually defined all structure for about spectrum management for radio astronomy. And we have recommendation which define preferred frequency band for radio astronomy. Then when we need to protect radio astronomy, of course, we need reference antenna pattern. And then a number of recommendations about sharing conditions, like protection criteria for recommendation array 769. It's very important, especially for telecommunication people like me, because it's actually transfer from Kelvin to the dB, because if you say something to radio communication engineer in Kelvin, they will not understand you. Then again, very important recommendation, array 1513, levels of data loss to radio astronomy observation. By the way, this morning I have heard a presentation, somebody mentioned that with processing radio astronomy can mitigate data loss up to 39%. I could say that if our friends from mobile society will listen it, they will be very happy. You will have no spectrum at all. So please don't show this presentation this morning to somebody to telecommunication world. Okay, and so if you're interested, you can find a link to all this recommendation. And this is the main problem of ITU. So I see that radio astronomers discuss a lot about new requirements for new protected spectrum. But the problem is that all these players, they involved in spectrum use and very much depend from this. So of course, defense, I've been really surprised that in some countries, up to 60% of spectrum is reserved only for military. And commercial telecom is growing up. They would like to put off satellite station everywhere on the satellite everywhere. And it's very difficult to find common language. So this is why I put this picture, because it's very similar with Tower of Babel, because a lot of people and a lot of lobby, and you can imagine that support, commercial support and support during the conference for example, for commercial telecom or for even transport system, it's much more higher than science. And all this achievement which Boris has shown during his presentation, it's only because of very hard work of very limited number of people. Some of them they're here, but it's really big achievement. And what we can experience because of new topology of the new networks, we have more and more cases, unusual cases of interference. So first picture, you can see it's interference from broadcasting satellite to passive sensor receiver. So of course, for the time being, this band is used. Oh, I finished. Okay. So as I can conclude the slide just to say that we have more and more new interference. So because we have a lot of radio system which are used for non-specific purpose, like in the middle slide is a picture. Now in new generation of civil aviation, a lot of cables which are on the plane will be changed for radio system. And we make simulation when all these new planes will be in operation, what will happen in the band where they work. So it's exceeding of temperature about much more than expected by other services which are using the same band. And of course, unintended electromagnetic radiation, you can smile, but this is picture of from satellite. It was unintended electromagnetic radiation from the setup satellite receiver because of very bad connection on intermediate frequency. And future, it's very good, I believe, US movie, Don't Look Up, I believe. And I borrowed a picture that when engineers speak with bureaucrat, so the answer is that after all calculations, then the miracle has to occur. So we have, first of all, we have a good system for interference reporting. So if you experience some interference, please report to ITU, first point. And I don't know how it can help international radio monitoring system, but even through ITU, you can have assistance in defining source of interference. From my personal perspective, the best way to proceed is cooperate with your national telecom administration authority, because they have to understand your interest during the conference, World Radio Communication Conference, because it's not ITU, but member states who finally make decision. And please participate in ITU work study, because number of participants in 7D is very limited, about, I think, no more than 20 people. And without their work for preparation for the conference, situation with the use of the radio astronomy bands will be much more worse. And what can help, again, I noticed during this meeting that maybe you have to work to speak more about money, just to bring your managers to your state, how much it costs interference for radio astronomy. Thank you very much for your attention.
Thank you. Any question? If not, we thank all the speaker for this session, and we have a 30-minute break, and we'll continue the session 3:30. Thank you. What's time? Oh, you, yeah, let me check. You 4:16 to 4:34. So that is about 15 minutes, 16 minutes. All right. Mhm. Okay. Now we should resume the next session. This will be the last session for the day. And the first speaker is Yidong Xu. Yeah, uploading. Okay.
Hello, everyone. I'm Yidong Xu from National Astronomical Observatory of China. And here I'm supposed to give an overview of a wide chapter that we are currently working on, which is about the radio astronomy from the moon. Yeah, that's the title of my talk.
Just a
And-
second.
Yeah.
It's not showing online. Yeah, just a second.
Everything okay?
Is it? Yeah, okay. Yep, let's go ahead.
How can I go back one slide? Yeah. Okay, so I'm going to have an overview of the white paper chapter we are currently working on. The title is Radio Astronomy from the Moon. And I would also like to take this opportunity to introduce a lunar orbit array called the Whole Moon Project. In English, it's called DSL project, or Discovering the Sky at the Longest Wavelength. So materials in this presentation are collected from our drafting group as well as from the DSL collaboration. So why going to the moon? So we know that the astronomy has taken this observation over a very broad electromagnetic waveband from radio to infrared, optical, up to yeah.
Second, there is a technical problem. Okay, yep, go ahead.
Okay, thank you. Due to the ionosphere absorption and the reflection and the really strong radio frequency interferences at the very low frequencies, we still have an observational band that is not explored up to date. That is the ultra long wavelength band or the frequencies below 30 megahertz. And this is the last unexplored electromagnetic window up to now. And so we have to go to the space to avoid the distortion by the ionosphere and to avoid the radio frequency interference on Earth. So several efforts have been made early in 1970s. So from the IAU experiment on the lunar orbit, it's revealed that the moon can really shield the radio emission from the Earth. And the backside of the moon can give us the most ideal radio quiet environment for our radio astronomy. And especially this is the sky map obtained by the IAU experiment. We see that has a very low resolution. We cannot identify any sources on it. And unfortunately, this is still the best sky map we have at these low frequencies. So it is very, it's time for us to consider some space missions to take observations from the backside of the moon to explore the ultra-long wavelength sky. So what to expect at this ultra-long wavelength sky? So this is a very unexplored window. So any new window opened to us has revealed the new phenomena and the new physics. So the most exciting science we could expect is the unexpected. And for the expected sciences, among those what we can expect, the most significant one may be the dark ages and the cosmic dawn. The dark ages and the cosmic dawn are the initial stages for the structure formation, and the currently known technique to probe this epoch, the only one we know is to use the 21 centimeter line from neutral hydrogen. And so the 21 centimeter line has a rest frame frequency of 1.4 gigahertz, and the signals from the dark ages and cosmic dawn are redshifted to the very low frequencies. And the 21 centimeter signal from the dark ages are redshifted to tens of megahertz, and the only site that is possible to detect this signal is the backside of the moon. So by measuring the primordial non-Gaussianity of these density fluctuations that is imprinted on the 21 centimeter brightness, we will be able to answer the most fundamental question in cosmology, that is whether the inflation really occurred a long time ago. Especially the large comoving volume that is available only at the dark ages give us very rich information of the primordial density fluctuations. And the signals from the dark ages are the only the only signal that we can expect to constrain tight enough for the inflationary physics. And the lunar far side is the only side we can attain such sensitivity. And the signals from the cosmic dawn would be have much more richer information of the first galaxy formation. And there are a large number of ground-based experiments there aiming to detect the 21 centimeter signal from the cosmic dawn. In 2018, the EDGE experiment has claimed the first detection of this absorption truth possibly originated from the cosmic dawn. But the measured signal is surprisingly large as compared to the expectation from standard cosmology. And later in 2022, the SARAS experiment have made a non-detection of the signal at a similar band. So they excluded the cosmological origin of this signal from the EDGE experiment. So currently, the measurement of the global 21 centimeters spectrum from cosmic dawn is still unresolved. So while these all ground-based experiments are struggling with these ionosphere effects and IFI on the Earth, some of the proposals have been made to take this observation at the far side of the moon. These include the DEPR project proposed by the US group, the Homon-Chihuahua or the DSL project proposed in China, and the Indian Pratyush experiment. Hopefully, in the near future, they will make independent measurements of this global signal from the cosmic dawn. So besides the very distant cosmological signal, if we have a large array for these ultra-long wavelengths observations, we can make a high-resolution map at these unexplored wavelengths. And from this high-resolution map, we will be able to compile the first source catalog at this new observational band. In particular, because of the spectral aging effect, the ultra-long wavelength spectra probes the oldest part of the structures in a galaxy. So this ultra-long wavelength observation could constrain the age of very ancient sources. And also the radio emission from galaxy clusters can be used to constrain the magnetic field and the acceleration of energetic particles in those galaxy clusters. And beyond those individual sources, the most important thing may be to map precisely the foreground of this ultra-long wavelength sky. And it is very, there's some unique feature can be expected at these ultra-long wavelengths. That's because at these low frequencies, the free absorption effect cannot be neglected. And this free absorption is only important below frequency about 10 megahertz. And this is what we have to take into account. And this is a prediction from a sky model that take into account the free absorption effect. And we can find that the sky map is very different from what we have at higher frequencies. Especially, we could expect a darker galactic plane because of this absorption effect. And this is unique. And actually, no one knows what it would be look like at this ultra-long wavelength sky, and hopefully in the near future, the radio astronomy taken from the backside of the moon could tell us. And another very interesting science case for the lunar-based observation is to understand the interiors and habitability of exoplanets. The radio emission from exoplanets are expected to originate from the cyclotron emission, and any detection of these radio signal from these exoplanets would be a clear indication of the magnetic field. And especially the magnetic field is very important for the habitability of exoplanets because they need this magnetic field to confine the atmosphere. So any detection of this radio emission would be a clear indication of the habitability of exoplanets. And taking the solar system as a reference, and this is the spectrum of this planet spectrum. And we see that only the Jupiter can be accessed from the ground. They have it has emission at relatively higher frequencies. All the other planets would need space-based experiments, which need to reach very low frequencies. And we would expect a similar situation for any exoplanets. And the ultra-long wavelength astronomy is also very important for the solar physics. By measuring these radio emission from these solar bursts, we may be able to constrain the structure and the propagation of this coronal mass ejection and constrain the acceleration and propagation of these energetic particles from our sun. And another science case may be more challenging is to detect the radio spectrum from ultra-high energy cosmic rays. The strategy is to use the whole moon as the target moon medium to detect the Ascarian effect. So radio pulses could be detected using these lunar-based telescopes. And the advantage of these putting these telescope onto the moon is that being much closer to the moon, the signal level would be much higher than any ground-based experiments. So hopefully I have convinced you that there are many interesting sciences and important science cases we could target for these ultra-long wavelength sky and to use experiments at the backside of the moon to take this opportunity. And currently, actually, we already have many experiments launched or planned in the near future. So first of all, we have the NCLE. It is Explorer, a radio instrument on board the Queqiao, the relay satellite for the Chinese Chang'e lunar landing mission. And unfortunately, the signal obtained by these instruments is dominated by the radio pollution by the Queqiao itself. So because this Queqiao experiment was not designed for this radio quietness. And then we have the ROSIS. It was launched earlier this year by the NASA's Commercial Lunar Payload Services. It managed to land, but sideways. So, but it is believed that some important data has been taken by this experiment. And then in the near future, we will have the Sunrise. Actually, it is not a lunar-based experiment, but to be more complete, I just put it here because it's a very important low-frequency experiment for the solar physics. It will image the sun at the very low frequencies and to provide very important information about the generation and the propagation of those energetic particles from the sun. And then we will have, so this is, the Lucy Night is another fully funded mission that could be launched in the near future. And it is a pathfinder for the dark age science from the far side of the moon. And also being global spectrum measurement, several other experiments are proposed to take this observation on the lunar orbit rather than landing on the moon. There's some advantages for these lunar orbiters because we do not have to land. That makes some things easier. And because the lunar orbit period is only a few hours, so the normal solar power could be used. They can take observation when it orbits to the backside of the moon and transfer data back to the Earth when it moves to the front side. So there's no need to put any other relay satellite for it. And the more ambitious telescopes have been proposed to make use of the more stable surface of the moon and to build much larger telescopes or arrays sky survey. These include the LCRT, the Lunar Crater Radio Telescope, the Astronomical Lunar Observatory, that's from Europe, the FarSight and the FarView from the US, and the LaRAF from China. And Shirley will give more details about the LaRAF experiments. So to really reach the signals from the dark age, so we would need a square kilometer array on the backside of the moon. This is very ambitious. So for the relatively near-term mission that is has more mature technologies, we have proposed the DSL project, or Discovering the Sky at the Longest Wavelength. It is a lunar orbit array consisting of one mother satellite and the 9 daughter satellites on a circular orbit around the moon. One of the daughter satellites will carry a spectrometer to, and it is dedicated to measure the global spectrum from the cosmic dawn. And the other 8 daughter satellites will form an interferometer array, the moving array, to make the first high-resolution sky map at the ultra-long wavelengths to open up the last unexplored electromagnetic window. And at the same time, they will observe the sun and the planets to uncover the dynamics of the interplanetary space. So I guess I don't have time for these details, just to highlight some science that could be enabled by this lunar orbit array. First of all, we have made this simulation to reveal that we will really be able to extract these 21 centimeter signal from the cosmic dawn using these high frequency daughter satellite. And we also developed the imaging algorithm and applied to that imaging algorithm to this lunar orbit array. And we found that we can really make images using these 8 daughter satellites. And we can also make some estimates for the sensitivity of this array. This is very promising. How much time do I have? No? Okay. Then I just jumped to the final slide here. As we are heading to the moon, it is really very urgent to protect this shielded zone of the moon. And the ITU regulations have already defined the shielded zone of the moon. And there are still some issues because these regulation does not apply to space research, and the exact level of harmful interference allowed is not well determined. So that's what we need to do in the near future. Thank you. Thank you very much.
Thank you. Anyone have a quick question?
Yes, thanks for the nice talk. I have one, maybe I missed. So what's the expected resolution of the home run project?
Okay, so it depends on the longest baseline. So we have the baseline from 100 meter to 100 kilometers. So with 100 kilometer baseline, the resolution at 1 megahertz would be 0.2 degree, and the resolution would be higher for higher frequencies. Yeah.
Okay, let's move on to the next speaker. Thanks, the speaker today, Joe.
Okay, thanks to the organizers for inviting this presentation, and I hope they don't regret it. I will carefully button, my asbestos-lined jacket as the slides are coming up, and there is fine print that I want to make sure you're aware of, which is if I happen to make an editorial comment or offer an opinion, those are mine and mine alone, and do not represent NASA, nor Caltech, nor JPL. So I'm going to talk about the promise and peril, and you'll see a certain synergy between my talk and the previous one. I'm trying to remember my first slide, in fact, if I can keep going without the slides. Okay, yeah. Oh, wait. Okay, so radio astronomy in space, we've just seen a version of this figure, but actually space is hard. Getting to space and operating things in space is really hard, and why bother? To one significant digit, my estimate is that we're doing something like $500 million or 500 million US dollars on ground-based radio millimeter, submillimeter, and actually, ALMA alone is more than that. So this is probably a wild underestimate. It's probably closer to 1,500 million. Why go to space? It's a lot of effort, and we've got a lot of metal on the ground. We just heard, there are bands at particularly at the longer wavelengths that do not penetrate the Earth's atmosphere. I'm not going to talk about it, but there are also bands, say, near the water vapor at 22 gigahertz or up at 60 gigahertz that do not penetrate the Earth's troposphere. And therefore, you have to go to space to observe at these bands. Okay, so the ionosphere, most of the science focus, when we think about going to space-based radio astronomy, it tends to focus on 30 megahertz. The one perhaps notable exception is the recent interest in going to space for Event Horizon Telescope or Event Horizon Telescope-like observations, but I'm not going to touch on that. Okay, we've seen examples of this. The lower left is one of the data sets returned by the Radio Astronomy Explorer, which shows pretty dramatically in the middle. Let's see if I do this. In the middle, here's the spectrum that the satellite detected when it was in view of the Earth. When you put something like 1,800 kilometers of rock between it and the Earth, it becomes very quiet. This is taken from the US FCC spectrum allocations, but these are the bands that are notionally allocated, or actually I think recommended as the official term for radio astronomy, and the rest are other services, other users. I think it's notable, what the Apollo missions called loss of service occurred whenever the command module went behind the Earth. And I have the impression from reading some of this stuff that astronauts actually kind of liked that. Okay, so why go to, and damn that got swapped, but you don't just showed an example of that figure showing the spectra of the various planets in the solar system. So there's compelling science of going to space. I'm not going to repeat that other than to emphasize the point, for instance, in the context of planetary radio astronomy or extrasolar planetary radio astronomy. We did not know that the Earth is a natural radio source until we got to space, until the very first satellites went up and detected the Earth's auroral kilometric radiation. Okay, there have been lots of concepts, and they date back. One of the first concepts, or one of the first discussions of radio astronomy and space, radio astronomy and moon, actually predates the Apollo mission. So people were thinking about it very early. Just saw a nice version of many of these pictures. I think this one is taken from a 1990 Scientific American article. Okay, so why bother? Well, there's compelling science to do it, and there are actual technical, or if you will, observational reasons to do it. You can't actually do it from the ground. Okay, now there's actually potential science contention here. And I think I'm sort of struggling for the word, but I think science contention is the way to describe it. The Apollo missions, or at least Apollo 15, flew an Apollo lunar sounder experiment. And since then, there was one on Chandrayaan-1, the Japanese Selene, what I would call Selene or Hyuga mission carried one. And the concept's pretty simple, and it's got a wide variety of uses even here on Earth. You have a transmitter, a radar transmitter here, and the reflection is off not only the lunar surface, the surface, it actually reflects off the subsurface as well. So in the case of the Apollo missions, there was a transmitter at 5 megahertz, looked like an interesting frequency, 15, 150. And they were interested, they had a specific objective to determine what the extent of subsurface discontinuities are. And actually, again, I would emphasize, there's serious lunar science here. And I think I'm about to show you an example of what the lunar equivalent of geologists would call stratigraphy. What's actually how the layers in the moon have been laid down, say by previous volcanism on the moon. Okay, so here's actually an example, actually taken from the U2 Chinese-led U2 rover. So the rover drove along for a distance that was something of order 1 kilometer. It had a ground-penetrating radar on it, and you can see in this case, actually, it had 2 channels, one at 500 megahertz, one at 60. My understanding is the 60 megahertz channel that kind of didn't work well, and so this is 500 megahertz. But essentially, the rover's going along, it's transmitting down, and then by looking at the return signal, you can figure out what does the subsurface look like. Here you can see the all of this structure here is some kind of subsurface below the surface of the moon going down something of order 10 meters. And then the paper actually, so that they can pull out so here's the surface in this sort of cartoon or scenario. The authors could actually pull out that there are half a dozen different substructures or different layers beneath the track that the U2 rover took. So actually, there's an issue here, and I couldn't find the perfect picture. I'd seen it once, but this is, I think if you go back to your copy of Jackson's electrodynamics, if you put an antenna that is on, a half plane that is a dielectric and a half plane that's a vacuum, the antenna, the gain is actually directed down. So you're most sensitive looking down for such an antenna. And I'll just point out, this was a project on which I worked called the Dark Ages Lunar Interferometer. There are various versions, and if you remember the pictures that were shown, a lot of the concepts involve antennas that are essentially on the lunar regolith or just above it. They're essentially looking down into the moon. They're not looking up into the sky. And when I was working on this, I was like, well, okay, yeah, that means, the maximum gain is that way. We'll just throw more antennas at it to compensate for the lack of sensitivity. In fact, actually, I should point out, this is somewhat of a digression and yet not. This is a concept, petals. This is actually a ground penetrating radar concept on the moon. So a group of authors, they actually got some NASA funding to do a study of how would you study the subsurface of the moon from a lunar science perspective? And they involve rolling out antennas, and here's in fact their cartoon of what the subsurface looks like. And I want to point this out in the sense of, if you think about the wavelengths that we're talking about from a science perspective, we're talking about tens of meters to 100-meter wavelengths. And that means, and the moon is very dry, the top layers at least are very dry, which means there's going to be substantial penetration. So, going down a kilometer is not a crazy idea. In fact, the Mars-Charad radar, so that one of the Mars orbiters carries a radar that operates at something like 15 megahertz, and they get kilometer penetrations at, I think I want to say like 15 megahertz. So here's a concept, and actually, if this movie works, it looks, their concept looks suspiciously like one of the concepts that we were looking at at the time. So what you're about to see here is this is a coiled up antenna, and we were just looking at the deployment. So this wasn't actually outfitted with an antenna receiving system, but it was illustrating here's how you would deploy an antenna from a lander, trying to prove out that concept. But in any event, I found it, I was not searching for this, but I stumbled upon this idea of, yeah, we can do ground penetrating radars looking, using the kind of systems we're talking about for radio astronomy. And in fact, it kind of raises the question, if you think back, if you followed the literature, one of the issues with some of the current dark ages or 21 centimeter cosmologies, and notably one of the contentions associated with the EDGES result is the extent to which the EDGES antenna was interacting with the subsurface in Western Australia. So do we actually need ground penetrating radars working at these frequencies to characterize the subsurface in order to do the science we're trying to do? And also, do you want to find out about polar ice deposits? There are lots of people who are very interested in finding out polar ice deposits. Are we going to end up with a lot of ground penetrating radars or lunar ground penetrating radars flying around the moon, trying to figure out what's going on with lunar ice, because they pretend, other people want to use it either for, actually, they may want to do it for science reasons. They may also want to use it for fuel or for keeping, astronauts or taikonauts alive. Okay, so what does that mean for lunar radio astronomy? We may have, the science contention is the lunar radar, the ground penetrating radar, that's a legitimate science question. We may actually need it. So how do you balance those competing science interests, and to say nothing of the prospecting ones? I'm going to touch a little bit too. I'm involved in the Sunrise Project, and when I say space is hard, it's actually it's impressively challenging. So this is the Sunrise Space, one of the Sunrise Space vehicles, before it was all packaged up. one of the things that I certainly did not appreciate coming from a ground-based radio astronomy background. That's our science payload. It's actually right here, the antenna is stowed, and then this is the receiver. All the rest of this is the stuff that we take for granted on the ground. So do you want power? You got to carry that with you. You got to carry that with you. So really, of this something like 14 or 15 kilogram space vehicle, only 10% is science payload, because we need to carry all this other stuff. One of the other interesting things too and this actually connects to the whole spectrum allocation question. When I was a naive young ground-based radio astronomer, I sort of said, well, okay, so Sunrise wants to observe roughly 10 megahertz, right? So let's go 10 megahertz bandwidth, 2 polar. This is pretty simple by ground-based radio astronomy. And I said, so you can work out, what's the data rate? And the telecom engineer at the time, she laughed at me. I think she nearly fell off her chair laughing at me. She's like, you're going to get 2 megabits per second. And that's not a technical limitation, at least not with this spacecraft. It's a spectral regulation aspect. Given the power that we have and given the allocated bandwidths for downlink to the ground, we get 2 megabits per second, which is actually a bit painful. But it's a weird aspect of the whole spectrum. I'd like to have a lot more bandwidth. I'd like to have a lot more data. And I want to emphasize this will come back to when Yudong made the comment about space research. That's the service that actually is used to transmit data like science data around. So we actually have to play with the space research band as well. And this is a confusogram, but it's a recent paper that shows your data rates, which I think, we're talking about some pretty serious data, potentially serious data rates. Well, that's an immediate driver. That puts an immediate requirement on the comm system of your spacecraft or of your vehicle. And your comm system actually drives how much thermal management you need, how much power you need, potentially structure. So it's this, very complicated, but essentially you get down to here, cost, and you do anything to the comm system and you end up with potentially driving cost. The other aspect, and I've come to appreciate this only recently, we're doing impressive things on the ground, right? But these are significant infrastructures. You heard in the previous talk, a square kilometer on the moon. That's serious infrastructure. And in order to do some of these ground-based telescopes, we've had to depend upon other infrastructure. So you depend upon, say the power grid or a fiber network in the Netherlands to get LOFAR to work. The entire process of putting in radio systems, radio astronomy systems in Western Australia. Part of that was going to a various description of either green Earth or brown Earth, but essentially building up the infrastructure, and that has to be done. If you want to be serious about doing it on the moon, it has to happen there too. People are thinking about that. Now, these are comm concepts, communications concepts. What do you need for communications concepts? And they're non-trivial, right? You see a lot of vehicles, you see a lot of space research band usage, beaming radio frequencies all the way around. I didn't get clearance to show it, but you heard reference to it on the previous talk as well. Power switching systems or power supply systems are notoriously noisy, and they can emit outside. They can produce, I believe the term is incidental emissions. I believe that's what we have on Sunrise as well. So we have a comb of emission generated by our space vehicle that is at something like 80 kilohertz or 100 kilohertz separation. And I still have a minute or something. I still have a minute. Okay. So for the Sunrise case, it's not a big deal because Sunrise is in this really weird situation, which the solar radio burst, we're actually operating in a signal to noise ratio larger than 1 situation. The solar radio bursts are stronger than the galactic background. So if we lose 80 kilohertz of bandwidth, here and there, it's not a big deal. But if you have an 80 kilohertz or 100 kilohertz or a 500 kilohertz comb spread throughout your entire bandwidth, we now have to deal with processing that. And how does that actually work? So in fact, let's see if my slides advance. So this is everything I've told you or I hope scared you about in terms of we have really compelling science. I think going to space, that is clear. But I think, getting to some of the engineering details, I haven't even talked about thermal management, but getting to some of the engineering details, particularly associated with the moon, be scared, be very, very scared. Thank you.
Thank you. Anyone have any question?
Everybody's so shell shocked. No.
Anyone
We have one. We have.
Oh, there's
yeah.
one.
Joe, very nice talk. But I want to see this. So you're saying that the beam is pointing downward on the lunar surface. However, if the downward doesn't have much emission, then effectively you are still receiving much more of signal from the above.
That in some sense that's true, but think about, let's look at this example here. That's being illuminated by, let's use the dark ages signal. So you're talking about 15 megahertz. So the sky is 100,000 Kelvin or something in that neighborhood, or tens of thousands of Kelvin. So you've got this structure being illuminated and multiple reflections by a 100,000 Kelvin illuminator. And you're now going to be able to say to our larger astronomy colleagues that we can seriously pull out a 10 millikelvin signal amidst all of these multiple reflections from 100,000 Kelvin illuminator. It may be possible, but we should not kid ourselves. It's not simple.
Okay, thanks. Next speaker. Yeah.
Okay, I'm Xuelei Chen. I will present a talk on large-scale array for radio astronomy on the far side of the moon. That's a project we proposed for the lunar surface-based radio astronomy array. So this is a work from our group, including myself, Fengquan Wu, and many other peoples. And also a collaboration from Professor Feng Gao and Professor Ye Chizhang and many other people from the Beijing Institute of Space System Engineering, the Chinese Academy of Space Technology. So I'm a radio astronomer, so I work on the radio side, whereas these colleagues work more on the space technology side. Let me see, how do I? Oops. Oh, okay. Okay, so already Yidong and Joy have gave a very nice introduction about why we want to go to the moon to doing these things. So I will not dwell into this. It's just that the moon can shed a lot of these radio frequency interferences. And this has been demonstrated by the measurements from the IAU satellite in the 1970s. But more recently, we have launched piggybacked on the Chang'e 4 mission, the Longjiang satellite. It also demonstrates this. So it seems that the far side of the moon would provide a perfect environment for doing radio astronomy. And we will look up to open up this new new band to discover new things. So I will skip this. So for me, a cosmologist, I'm most interested in looking into the primordial fluctuations. As you know, if you want to really test inflation or other theories of the origin of the universe, you can try to measure the primordial fluctuations, which preserve the information from this extremely early time. However, these are in order to get really good statistics, you need a large co-moving volume, and a very large part of that co-moving volume is in the dark ages. And also you want to look for the primordial fluctuations before its evolution. So that's why you really want to measure the whole information in the observable universe in the co-moving volume. However, the problem is that these fluctuations, although they are reflected in this 21 centimeter fluctuation, the noise is very large because at the low frequency, we are dominated by the sky temperature, and that scales up as we go to lower and lower frequency. So this is from our simple prediction. So you see that even with a 10 square kilometer array, 1 year integration and 1 megahertz bandwidth, you still barely measure the power spectrum. So this really requires a lot of technical progress in this. So Yidong have already showed this study by lead by Liang Cooperman et al., which shows that you really, well, to start up to probe these primordial fluctuations, you already need a kilometer square kind of array, and really you need to even larger arrays. But we can work towards that direction step by step. So Yidong already showed that a number of these projects here for the lunar orbit project, our own group, including Yidong, me, and other people, have been working on this DSL, and we hope that this will be soon be realized. But there are also other proposals, such as Stepper or the Cosmic Cube or the Pratush and SIM. But also for the lunar surface, there had also been many interesting ideas. Now, the lunar orbit, I would say that engineeringly it's simpler because you do not actually need to land, and you can use the solar power to power the whole system. Because the satellite will complete one orbit within a few hours. However, for the lunar surface, it has some advantage because it has a stable platform. So it's easier if you really want to go to very large arrays. So there have been many such interesting ideas. For example, there could be reflectors, which Joy also showed some pictures, nice pictures from even early time. And you could, because we are at low frequency, we can use a simple form of the antenna construction, such as thin rod, wire, or membrane. We probably need to go to at least 10 kilometer baselines to have an angular resolution. And the site condition, we want to go to the lunar far side, middle latitude, and polar regions, or polar regions. And the near side could also be used for some testing. Currently, I think with the reasonable technology, we can probably use 1 or 2 rocket launches to realize an array of maybe 10 to the 2, well, like hundreds of units. Here are some of these antenna concepts. Okay, so I want to mention that so this membrane antenna may be a very interesting direction because it's very light in weight. Besides realizing arrays, they can also be used to produce the reflectors. I show a picture taken by, well, a picture generated by Professor Huilong Zhang to showing that you can easily reconstruct a reflector using these membranes. Now, the questions, however, is very hard because scientifically, in the near term, we probably can manage 1 or 2 launches, but probably not like hundreds of rocket launches for these projects. And then what is the most attractive science publication for such an array? If you have only like a few hundred dipole antennas, which still has a effective area much below the kilometer square. So it cannot be used to probe primordial fluctuations. what will be the interesting science here? And then you also need to solve a number of technical problems, such as how to effectively produce the antenna, what is the material, and your electronics can have to survive and work in the lunar environment. And also, how do you supply the power, transmit the data, deploy the array, and the non-flight terrain and underground inhomogeneity, which Joy mentioned. But anyway, we need to test these things. So I will not, so these have already been reviewed by Yidong, but let me just mention our own project. This is the full author list, and the paper has been published in the Philosophical Translation A. Its acronym is LARAF. So basically, we want to set up a master station at the lander and then 20 to 30 stations around it. Each station may be having something like 10 or 12 antennas to generate a total of about 200 to 300 antennas. And we use the membrane antenna. So I will skip the science, but here I show some of the features that the antenna is made by conducting layer along the membrane. And we arrange them in a spiral form so that they have a nice beam to survey the sky. And we can use a rover to go along the different directions to deploy them, and they are connected by the membrane containing the optical fibers and connecting wires. So we probably will going to do the observation during the lunar night. That avoids the problem of heat dissipation, but it does require a lot of energy storage. So we have studied various forms of power supply. These are mostly my colleagues in the space technology, and they come to the conclusion that the regenerated fuel cell is probably the best solution in our case. We have chosen some particular sites, but of course, there are many other sites as well, and we come up with a mission profile. We have also done some testing for this membrane. I will not, well, these are the simulations, and we have also done some ground testings. I will not have time to do that, but I can show you that we have published a paper in this newly produced journal, and I put some of the magazines there. If you are interested, you are welcome to take them. And okay, finally, let me just conclude that I think probably we will begin to do lunar astronomy very soon. We will probably within this decade to realize a few satellites or lander to do a first step image or spectrum for the sky. And then maybe the next decade to do some hundreds of units to deploy on the moon. And finally, I think in the future, we will move to the eventual goal of probing the primordial fluctuations. Thank you.
Thanks. Quick question, one quick question.
You suggested locations at the poles. Isn't there interference from the Earth coming there by diffraction as well? Isn't mid-latitude the only place?
No. So for the LARAF project, we are proposing, we are not for the poles. We are aiming for the mid-latitude. But what I'm saying is that currently there have also been idea of deploying some array in the pole so that, of course, the Earth is just above or below the horizon. So you need to find some terrain, maybe a little hill to kind of block or mountain to block it.
All right. Well, thanks, the speaker. And we will have a last speaker for the day, Federico.
All right. Thank you. And while the slides are coming, just to let you know that I'm not on the moon. So sorry about that. Right. So yeah, this is what I came out when I was thinking what to talk about in this session. And I think I'm happy with my choice. I think it makes sense on all the discussions you guys been having. I'm sorry I missed some of them. And yeah, I think it's pertinent, right, to ask, can you really access the full radio spectrum? And you'll see why. You might be a little bit angry at me, but let's have a discussion on this. So I don't think I really need to explain this to you, right? So everyone understands this, how radio astronomy sees the radio spectrum, how much of the radio spectrum you really need to access. Full disclaimer, I'm an engineer, not a radio astronomer, right? So I try to understand what you guys do. I try to keep the radio spectrum clean for you. I should have said I'm spectrum manager at the SKAO. So I really understand why you need to get as much as the radio spectrum as possible, okay? But how do other users of the radio spectrum see it, right? We all use these things, right, from a start. So we use for communications, we use it for measurements, we use it for remote sensing. We were talking about the moon and we need to get the data back from the moon. We use it for medical applications, right? We use the radio spectrum for a lot of stuff, right? And you see some graph in there and you of course know how the radio spectrum looks like. But this is how the ITU, the International Telecommunications Union, sees the radio spectrum. Several people show these very nice and colorful pictures. And the reality in there is that between these frequency ranges, there you have the percentages of the allocated frequencies to radio astronomy on a primary basis, right? So what that is telling you is that, for example, if from the Earth, you want to have a receiver from 30 megahertz up to 300 megahertz, which is roughly the frequency range of SKA low, I'm not going to be popular with my boss here, you have 2% of the radio spectrum that is protected for radio astronomy internationally. Right? This is what this means, okay? And also so on the other frequencies, and you see that on the very highest frequencies, we are in a much better position because some time ago, when all these bands were allocated, I think radio astronomers were very clever and they say, we want to use many, many frequencies in there. So we got them. There are some caveats in there. It's not quite like that. So, but in higher frequencies, there are many more bands assigned to radio astronomy. And you see it's all those yellow little bands. Those are allocations for radio astronomy, right? So you see there's only a few in lower frequencies. So going a little bit more in what does this mean, right? So Vadim was talking about the radio regulations. This is the international treaty that says how the radio spectrum is used, right? How it's divided, basically. And if you go there, this is a very, very long document, and it's written down by spectrum managers and lawyers and engineers. So it's a very complicated document to read. But you'll find tables like this one, right? With different parts of the world, basically, and frequencies in there. And I'm sure, of course, you recognize this frequency range, 1.4 gigahertz to 1.427 gigahertz. And this is a primary passive only band. This is the highest level of protection that we have in the ITU, right? And in there, you as radio astronomers, you should be always looking that this band is extremely clean, that you don't detect any man-made signal in there. There are some caveats, but you should start there, like saying in there shouldn't be anything in there, right? Then we have another set of protections, like for example, Vadim was talking about these ones like 5.149, that has much softer language, and this urges administrations to protect radio astronomy, right? You see of this language, a little bit confusing, but it's a lower level of protection, much lower. So if you find interference in your receiver that maybe starts up there and finishes down there, if you find interference there, it's not that clear that you can go to your national administration and complain that there is interference in there. And the last one is there are some bands which basically we don't have any kind of international protection, right? So we can do observations in there, but it doesn't mean that we can complain if some satellite or some Earth station that is communicated to space, for example, is producing interference in our receiver. again, there are some caveats in what I'm talking about. So I was talking about this, right? So we have the primary bands, also protected by 5.340, so only passive bands, then only the primary bands, and you can find this listed in some recommendations of the ITU that I'm sure after this you will all go and find, of course. No, okay. Then you have the secondary bands, we have lower level of protection, but are still allocated to radio astronomy, so are still very important. And then there are the 5.149 bands, which are basically saying there are some bands that are important for radio astronomy, we use them, but are not protected. And this is, of course, subject to national regulation of the radio spectrum, right? All of the ITU stuff is the international use of the radio spectrum, then countries apply the radio regulations nationally. Right? So it's always, you will see that some countries have different use of different bands, for example. And there you see some examples of these bands. So something I think is interesting is that allocations also have further conditions, right? One thing is to say we have this band protected for the astronomy, but there are some other conditions, right? They allow the interference levels, right? So you cannot say in the regulatory world, right? Bear with me here, as an engineer, you cannot say that there shouldn't be anything at any power level in this frequency range that is assigned to radio astronomy. There is a recommendation called RA 769 that defines what is the allowed level of interference that you can have at the international level. Also, there is a percentage of data loss, right? So if you're doing an observation in a particular radio astronomy band, you are required to accept a certain level of data loss due to interference. And there are also some others that list, for example, the frequencies preferred for radio astronomy. And I thought it was interesting just to stop a little bit, just a moment, in RA 769 and try to explain to you how this works. Right? RA 769 talks about the protection criteria for radio astronomy, and it defines the thresholds, right? And I tried to put it here in Jansky's for you guys. So if you see, yes, I don't talk Jansky, sorry. I talk dB watts or something like that. But the thing is, it's defined as power, right? It's defined as power in the radio astronomy receiver. And for that, you need to make a lot of assumptions, right? And I'm sure you're looking at this and you're doing the math in your head, and you say, well, this is not what we are doing right now, or this is not what my instrument does, for example. Right? So it's very important to understand that the regulation works in this way, right? So we have these recommendations. So when we go to the international regulation and the use of the radio spectrum, these are the limits that we use. And the way we calibrate it for flux is with a 0 dBi gain. So we think that the interference is coming from the side. And there are all the discussions about the satellites, and satellites are up in the sky. So we are looking up, and it's another discussion, all right? So as you see here, this is what you are thinking. And this is what the active users of the radio spectrum think every time they see this thing. They say, oh, how do we achieve this? Impossible. So we have all these fights, right? So there you see what's the fight in spectrum management. Also, RA 1513, acceptable levels of data loss. This recommendation says that we, as astronomers, I feel part of your community, we need to accept 5% from all the systems using bands outside of our band, right? So if there are out-of-band emissions, we need to accept 5% of loss of the data defined in different ways. So you can define it as sky loss or as time loss, 5% of the total systems, which is quite difficult to define, or 2% from one system. And for example, this led to the geostationary belt having a lower interference threshold, because basically if you think on the geostationary belt, it blocks a lot of the sky, right, on some frequencies. So if you're trying to observe in frequencies close to whatever is used from the geostationary belt, and you start getting close to the satellites that are there, there was a whole discussion in the ITU that ended up to the levels in RA 769 minus 15 dB, for example. So this is when you're starting looking up and you see that the levels in array 769 were defined from the horizon. All right, so what we all know, we observe also outside of radio astronomy bands, right? And it's important to know that from the point of view of regulation, this is opportunistic observation. Right? At least from the international regulation, this is opportunistic observation if we are using other bands that do not belong to radio astronomy. So that's what I said. And there is something we can do, and we do that, I think, very well in the SKA, in South Africa and Australia. So we are protected nationally by radio quiet zones. There are around 13 radio quiet zones around the world. And this work very well at the terrestrial level, right? This don't work so well when we are talking about satellites. And that's what Boris was talking about with some of these agenda items. So it's important to understand that internationally, no interference and no protection basis, that's the wording from the ITU, means no protection for radio astronomy, right? We are a passive service, so we can observe whatever we want, right? We can receive whatever radio signal we want, but the reality is that if we are outside of radio astronomy bands, we don't get any protection. Okay, so just to finalize, I wanted to talk about this on the future of radio spectrum. I think most of the people that talked about this went through it. So large satellite constellations, direct to the cell or direct to device satellites. Of course, this is tricky because it's bringing ground cell phone towers in space, and they could use many different frequencies. So that's a big concern for everyone. IMT always looking for more spectrum. We are seeing a trend, and I know some of the presentation talked about this, about dynamic use of the spectrum, right? Trying to start communicating with active users of the radio spectrum and seeing how we can enhance the use of the radio spectrum, how we can find time slots or frequency slots that are not used at some time that we can observe and then someone else can use. So there's a lot of discussion about this, very tricky, but maybe we are moving in that direction. And of course, everyone is talking about this. I'm glad I got to be last because I think those presentations were very interesting about cislunar space. I used to work in electromagnetic compatibility in space, so I do know how difficult it is to make a spacecraft radio quiet. And when I say radio quiet, I'm talking about radio quiet levels for communication systems, right? If you're talking about radio quiet for radio astronomy systems, that's many, many more kilos of shielding, or many, many more hours of thinking very carefully what systems will you use, right? You want to have an ADC to sample the signal that is being detected by an antenna on the moon. That thing is switching. If that thing switches, it will radiate. So it's a very, very tricky problem. So conclusions and suggestions. First of all, educate yourselves, educate your colleagues about the use of the radio spectrum, right? I'm not saying that you stop using all the frequencies you need to use. Just be mindful of how the radio spectrum is used, of what frequencies you're observing in. There were some presentations about not throwing away the RFI. Right? I know that you all do science and you want to focus on the science, but you shouldn't just throw away the RFI. You should try to understand what that RFI is, or at least find the person in your observatory that cares about it. Right? Contact that person and just chunk the whole thing of data to them and say, figure it out, but there's RFI. Because if you lose it, we don't know what it is, and we cannot do anything about it. So value the radio astronomy bands. Go back. You should really know where they are, right? Now you know that 1.4 gigahertz is a protected radio astronomy band, and there are several more. So you should know where they are, right? You should know that your telescope has this, and that protected band, and there are many more frequencies you observe, but these are the protected bands, and make sure there's no RFI in there. If there is RFI in there, you should contact your observatory. You should say, there's RFI in there, And we will try to figure out if that is really above the permissive level or not, and so on. But start there, no RFI. And I think there's an opportunity here, and I'm glad we are all here together, and this is a big crowd, that's great. So we should really be having a priority discussion on radio astronomy, on bands that are not allocated for radio astronomy. Maybe we have an opportunity here, right? Having a new allocation in the international framework is very difficult, but it can be done. Anything can be done. I'm sure Vadim will disagree with me, but I think if we have a science case, if we say this band is extremely important for radio astronomy for the future, maybe we can work on that. All right, so just to finish on spectrum management things, everyone mentioned these things, agenda items in ITU coming. If you know who your spectrum manager is in your observatory, or if you're working on this, focus on 1.13, 1.16, 1.18. And I would like to take the minute I might have to just make a remark on the use of the radio spectrum around the moon. I'm simplifying the name, agenda item 1.15. I hope I got the number right. There is a need, an urgent need, to put a document in the ITU system to define what the level of protection of radio astronomy on the moon is. Right? You've seen, I talked about RA 769 there. And if you see the thresholds in there, I think the RA 769 is this wonky curve. That's what we have right now for the protection of radio astronomy. And this is terrestrial radio astronomy, of course. But if there is no input in the September meeting of the Working Party 7D for radio astronomy, where we need to respond to another group, Working Party 7B, which is the group that deals with the agenda item 1.15. Sorry, go back there. If we don't respond something different than RA 769, RA 769, with its limits of a few tens of Janskis, will be what the ITU will think that astronomy needs as protection on the moon. Okay? So just to make it clear, it's not a threat, but now we really need to do that. And some of the people that are working in spectrum management, we mean well, but sometimes we don't have the technical knowledge of this. And it only takes someone to write down a 2-page document saying, these are the science cases we need to do, and this is the sensitivity of our instruments. If you see, and I'm sorry, I'm dwelling a little bit. I hope you don't hate me, Josh. There. So if you see how this was defined, it was looking at the 2000 second integration with typical system temperatures of systems, looking at the bandwidth of radio astronomy bands and using the radiometer equation. And then with that, we calculated the minimum sensitivity that can be detected, and the threshold is 10% of that. As simple as that. That's how the RA 769 thresholds are calculated. If you think that this is wrong, that we should do something different on the moon, you just need to sit down, write it down, and send it to some of your colleagues. You can contact me, you can contact Vol, you can contact Boris. There's several people here that do radio astronomy. There's the IAU group that's working on the moon. There's Richard there, and I'm sure many of you are also involved on that. So I think it's very important that you do that before 5 of September. Okay, which is, yeah, you have like 2 weeks. Come on, you'll do it. All right, so just to finish as a bonus, I took a little bit of time to do this. I'm not in the commercial area of the spectrum, so please bear with me if the numbers are not very good, but I tried to look at the cost of the spectrum. And I looked into here, I put the source because I tried to do it, but I don't deal with the cost of spectrum, right? We do science, so we don't sell the spectrum. But some of the auctions, for example, in 2023, you should know that the national regulators sell the spectrum, right? So if you're a commercial user of the spectrum, like phone companies, you need to buy the spectrum to use it. And some of the auctions in 2023 were in the order of millions, $300 million per megahertz, right? Or in India, in the 700 megahertz band, $500 million per megahertz. So if you think that we have in the H1, we have 27 megahertz, so we are sitting on $14 billion, right? And we should take care of them. All right? Okay. Yeah, don't think about selling it, please, right? Okay, so with that, thank you. Thank you very much for your attention.
Thank you. Anyone have a quick?
Sorry, I was running away.
Well, thanks for the nice presentation, and we hope that you remain part of this friendly community now that you've joined it. Your final slide, I think, although we all sort of laughed about it,
yeah,
it's actually fairly serious in the sense my limited interactions with ITU or with spectrum management have been that we often talk past other users of other services, other users of the spectrum. So I have, you talk to a satellite company, I want to, you have to comply with this radio astronomy thing, and their response is often, well, that's going to cost me a lot of money. And our response is, well, we're going to lose science. And lots of people understand, dollars and euros and yen and rand, and it's very difficult to understand science in a monetary sense. And so I think what you're showing, it would be interesting to hear if you've ever thought about beyond the bullet box or the bang box there. Is there a way to cast what we do in a way that a larger community than just a radio astronomy or science community understands? And I think, well, Josh is about to provide the answer.
So I think Josh is coming to answer. Yeah, go.
May I?
Yeah, of course.
So measuring the worth of fundamental research is pretty hard, but general relativity was first proven using astronomy. Now, 1/3 of the economy relies on general relativity, especially space travel. So we have to take into account time dilation in order to do space travel. What is this worth? Well, you want to know where you are. If you want to know where you are, you're looking at your phone or your GPS. It doesn't work without general relativity. So that's number one. Measuring this in numbers is not easily possible. Here's the other thing. We've been talking about geodetic VLBI. Now, geodetic VLBI gives you the rest frame, as we heard, with respect to space. The only reference system that is working to fix, because the Earth is moving all the time, so there's tectonic plates, blah, 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 and so on. We've heard that. Now, again, if we want to know where we are, we are relying on the satellites. The satellites can only fly if we have this reference system, and that relies in its precision, in the required precision, only on radio astronomical service, if you like. Charge $1 euro a year per phone. And there you have your worth. And that's more than that. Yeah? And that would be my first reply to that.
If I can chip in, trying to go for a more engineering approach, we try to start in the discussion of satellite constellation impact on astronomy. We try to start thinking on the operational costs and the capital costs of observatories. And that's something that could be done. But I think when we started getting to the numbers, it's not significant with respect to the global economy on the radio spectrum. And that's where you need to start arguing the things that Josh is talking about. That is much more, not only on the capital cost, not only observational cost, but also on what are we giving back to society. And it's very difficult to measure in dollars, I think. But please, if anyone wants to write a nice paper, maybe. Right? So, again. Okay.
Thanks. Yeah, thanks a lot. And this actually, I'm absolutely not angry, and Federico, for mentioning this the topic. So now we are coming to the final part. Hopefully, yeah, we've got 10 minutes, but we already had one part of this discussion. I just wanted to highlight again, and I'm pretty impressed actually about the number of people who have attended in this room. So there was also some fluctuation. So I think it's 100, 200 people that were listening to the needs to protect, or to our arguments to how beautiful our science is and how much we need to protect it. So again, we need to have all this networking and to have all this exchange between the different stakeholders in this game. And we all, as astronomers, need to be aware of that and keep this going. This is just one remark. And then luckily, Federico already made this argument, because I mean, this challenge here that I put out there first was exactly about having a look at the current thresholds of this recommendation 769. As far as I know, nobody wanted to have a craft pin. It's very, again, it was highly collectible. It would have been your chance, but in any way, I mean, we have the need right now to put numbers there. We're able to do this on our own, but we would like to have the backup of you. And again, look at this table. If you have a contribution, make it. The craft pin will find its way to you, right? And yeah, having said that, we will certainly try to take care, but this brings me to then also the next point. One of the things that we need to update regularly, even just to confirm, are these lists of the most important lines. So latest updates have been, well, 2023 actually for the left document. This is still an old image. But we need to have a confirmation by the IAU, by the astronomers, that these tables are still valid and still the most important lines. As Federico pointed out, there might be something might have changed in the past 10 years or 20 years in the case of the lower frequencies below 1 terahertz. And we need to review that. And actually, this question was actually the start of this focus meeting. We spectrum managers thought, okay, we need to have this updated. We need to have a discussion about it. And I'm greatly thankful that the resonance that we had here was so great. So there are the contributors to the science chapters. They are all thinking about this. And if you want to contribute, if you want to be part of this, and please be, then you can just write me an email and I direct you, or any of us, we can direct you to the right drafting group chairs. There are many aspects that need to be covered in such a study. Scientific, we did that. and also regarding the protection to show that we're doing the best on our side to protect the spectrum. Now for the remaining discussion, I propose to think about the three questions. So number one is, how do we identify the most important observing bands? How can we do this? I mean, technically, which gremium? The White Book is certainly a start, but we need to carry that forward. Maybe we think about it, maybe we articulate it loudly now. The one easy way to do this is certainly take these old lists, the IAU list of important lines, which are actually reflected in these recommendations that I have shown to you. Can we at least confirm them? And that would be the next part, as was also suggested during this meeting. And finally, as Federico also pointed out, currently there are still a few. And Vadim, you heard Vadim, there are still a few. In order to tackle the challenge to protect radio astronomy sufficiently, and actually to create a balance between the cost of protection and actually the cost of operating our great facilities. So how do we achieve this? Because we are quite a few, and I think we need to think about how to maybe improve this situation. So now, are there any comments with respect to these questions? Are there any comments with respect to any of the chapters that we had?
Thank you very much, Josh. Maybe I'll just try to kickstart the discussion. Even though I'm not a proper astronomer, I'm a physicist, not more general than astronomer. I would like to start with the first question. And actually, I would like to actually provide some comment that it is indeed important, and it's mostly up to astronomers. Of course, the nature defines it, so it's more like we need to just look at the nature, the spectral lines. I think they should be stable, at least as far as I know. They don't tend to change over time. I hope. Otherwise, the world I'm living is a lie. So I'm just what I'm trying to say here is that we already have a set of frequency bands, and as previous speakers said, some of these bands are purely passive, so they are not intended to be used by everyone else. And these bands are quite precious, and if we would, let's say, create another set of frequency bands for some reason that will not be in line with those bands, believe me, all other spectrum users would be extremely happy to see that, because that would be an opportunity for them to seize these bands. Because you have seen, each megahertz is really expensive. So if they can get it, they would be so happy, maybe the stock market would explode. So actually, what might be good here is to try to identify what is important outside of these bands so we can keep them. We don't want to, at least I hope you astronomers don't want to lose some bands. So maybe that would be a good idea. And a second comment, even if something would be needed to be adjusted, and from my personal perspective, I would say probably if something would require adjustment, maybe it's some bands for continuum spectrum. Again, I don't believe spectral lines should move anywhere. It's still a possibility. There is another service which is really close to radio astronomy. It's Earth Exploration Observation Service, which I guess we are not speaking here at IAU because it's observation of Earth. It's more about meteorology and weather forecasting. Nevertheless, they, during the last study cycle for in 2019 to 2023, they got an agenda item to adjust their allocations. So if we consider that it's really necessary, it's still doable. Though, again, I would advise extreme caution with this. So maybe just to help kickstarting the discussion. Thank you.
Yeah, thanks a lot, Boris. I mean, of course, we are very well aware of this, and I think we would be always be keen to make the community aware of the fact. Any Mike, other people?
I mean, yeah, that is obviously a conundrum, right? In that if you identify the rest frequency, well, it's great if you're doing galactic astronomy. The minute you're not doing galactic astronomy, it's a different band, and it'll extend all the way down. So they do change at time, and that's quite a conundrum for us to deal with.
Yeah, this is certainly one of the topics that need to be discussed in this list of frequencies, because they are restricted to actually galactic mostly.
Just wanted to say that I think the exercise that the radio astronomy community should do is not a Nobel Prize exercise, right? It's something very important, and I'm sure many people will not be convinced, but you need to do it, and you need to do it fast, right? So there needs to be a decision making on the importance of the bands, on identifying something new that maybe is not protected at the moment, and you really need to protect it. And there might be questions, but you really need to make decisions, right? And I'm saying this as an engineer who works with astronomers. So yeah, it's trying to take those decisions, and I think it's important to recognize that.
Willem, I think we will go a few minutes beyond the time.
Well, one thing, I'm an old timer in this business. I started out when Iridium was getting online, before Iridium got online, and we're still fighting it. And there is a little bit of I mean, looking back, I stopped doing a lot of spectrum management. There is one thing I would like to say, is that I see a nice crowd here. We should all get involved, actively involved, because I know it is a thankless job, very much. The colleagues don't appreciate what you're doing. They're actually downplaying what you're doing very often. I mean, the projects we did at Westerbork, I mean, the astronomers didn't even want to deal with it. Yeah, although there was a forward-looking, there is a general attitude that stick your head in the sand and we'll just edit it out and we forget about the problems. It's getting worse and worse and worse. And most people do not realize how bad it's going to be. Yeah, we are now in panic about the satellite systems. And yeah, we don't know what to do with it. And the optical people are even more concerned. Get involved. I mean, one of the things that I also realized is in, I think it was in 94 or 92, I wrote a footnote in 149, 149 on 6.7 gigahertz. And the recent decisions on this band, yeah, it's going to IMT, to things that we really don't need. Yeah, I mean, we don't need to talk to our refrigerators. I mean, this is, yeah. And so we are losing area, and we are becoming more and more sensitive. And so it's very encouraging to see all these young people here. You should get involved, all of you.
Well, good. Thanks a lot for this, Willem. So very, very appreciated. And I also think we have a very, very large crowd. Sorry, Boris was. Boris raised his hand first, so let's try to have both.
Okay, thank you very much, and I'm sorry for raising hand second time. I'll try to be quick with this. So just thank you very much for these very strong words. It's really indeed important, if I may say, from all this international regulation perspective. What is important is that whenever administrations arrive to ITU, usually their position is already defined by their country. So they don't, usually people who go there, they don't have much flexibility. Even if internally they agree with you, they are bound by decision of their country. They will never go against their own country because they were tasked to do a very specific stuff. There are different levels of participation. ITU is the highest one. There are lower ones like regionals one and national ones. And usually what you can find is that these people who are responsible to represent administrations are very flexible on a national level if you can come to them and tell them that it's interest of their own country to have this. And otherwise, whenever you go to ITU, you might find yourself speaking with a wall that is not really willing to understand you. And believe me, it's really hard to not just to convince, but also to explain something to a person who is getting paid not to understand you. So yeah, it's just to continue this call that we really need more people to get involved. We are trying really hard, but unfortunately, without your help from all countries around the world, at some point, we won't be able to progress much further with radio astronomy protection. Thank you.
Very briefly, I think potentially the question about what is the cost or how can we represent the cost of science is potentially only of value when decisions and trade-offs are being made. Once decisions have been made, there's a period where the decisions need to be enforced, sustained, etc. So I just wanted to put that cost question there. Really want to focus on sustaining. Federico mentioned something that made me think it's a very, very valuable thing. These are regulations, there's interpretation of this, uniform interpretation and consistent reporting against that interpretation is potentially a valuable strategy that we as the astronomy community have so that we have data on the table that can be consistently and accurately assessed and considered by these panels. Do we have that in place? Do we have a consistent interpretation of these regulations that we regularly evaluate at each of our institutions and contribute to the international panel so that they can report back and say, this is what, the 4% that has been allocated is being impinged on at these levels, at these institutions, and it's getting worse every year? Or do we have science studies that try to evaluate what is the most sensitive measurement we can make that is not relevant for the specification? So I'm arguing for making sure that we have standardized tests that we run regularly and report back as an organized community.
Okay. This discussion is going on. I'm sorry, it's so interesting.
I think it's nice, and please bear and keep asking things like this. We have a very, very hard time to find examples of measurements of interference in radio astronomy bands as spectrum managers. We have a very hard time on that. And I know that, for example, MERCAT stores quite a lot of information on the R5 flagging, but most of the observatories don't, and most of the astronomers don't care about it, right? They just flag it, throw it away, they do their science, which is understandable. But we lose the tools to argue that these bands are being eroded, right? The protected bands. The discussion on how we use the spectrum and how we interpret the spectrum or how we interpret the regulations is a much more tricky one because it depends on the national interpretation of the treaty, right? Different countries use the spectrum in different ways. So for example, in South Africa, you have the radio quiet zone regulations, which that protects a very big chunk of the spectrum, which doesn't happen in other countries. But definitely, if one thing we need to get out of this is that when you do your science, at least don't throw the RFI information away and find someone that cares about that. Maybe you don't do it as
because you're doing your science, but store that somewhere. And to answer your question, there's no standard for doing that. Definitely. I think we had some discussions with Davis 1 year ago about that.
Yeah, this is a very complex matter that we really need to address. It's great to bring this up. So there are subcommittees in our spectrum management organizations that try to deal with this stuff, but you can imagine that this requires also quite a lot of effort to standardize this, for example. Anyway, I think we need to wrap up. So a few final matters. Please send your presentations to me, this square here. I don't know if they are collected by the organizers of the General Assembly, but they are highly useful to us. So please send them to us. If you want to contribute to the white book that has been managed a few times, please contact me or contact this square here. The proceedings will be coordinated by the White Book Drafting Group chairs, and you may or will be contacted for your contribution in this. You may be contacted. One little disclaimer. So there are people in this audience organizing the RFI 2024, which is a very specialist meeting on spectrum management on an RFI. The register, I think the talks have been, here's the organization.
Sorry, I had no idea that was coming. So I'm the general chair of that conference, and technically the submission deadline has lapsed in about 2 weeks ago or so, but we are happy to accept more talks, interesting talks. We also have travel support available for those who need it. If you can't make your own way on your own dime to Bariloche, Argentina, a beautiful place, I'm hearing, please write to me or just register on the site to indicate that you will need travel assistance, and I will be in contact with you and to figure out how we can get you there. So please do sign up and submit your abstracts. Thank you.
Oh, that is word. Thanks a lot. Well, then one thing to just think about right now is when will we have the next meeting of this sort? Having astronomers and the specialists sitting nearby, close by, and pondering on these questions. Then another thing to think about is how do we carry it on in a more official way? If we want to make our results more official, we need to find a way to do that. Maybe contacting Commission before radio astronomy. And finally,
Sorry, guys, I just thought there's no URL. rficonference.org. With or without a dash, I've registered all the names. So rficonference.org, that's the URL to sign up. Thank you.
I missed this, but you see this. It was, of course, pretty silly by me here. You see this. It's a link. So in other words, I will put this on the Slack. We can still use the Slack for conversation and discussions. Now, finally, thank you all. Thank you all for being here. And this is actually a list of people who are involved in this focus meeting. And I was impressed myself. I mean, there is double mentions here. But I was impressed myself how much I had to reduce the type size to get all these people here. And this is, Willem, this is extremely encouraging, I think. And I think let's just carry it on, and let's see when we meet next time. And thank you.
Yeah, okay. So I think I've already told you that, okay, okay. I have gone back to China. So I have gone back to China. You know that I've already told you that. So actually I was wondering that maybe sometimes you can visit us in this institute, you know that? Is it possible? Would you like to visit us? Visit our institute?
That is, yeah, it's a very, very kind
And
offer.
yeah, probably maybe next summer. So Christine also is now in our institute.
Christine?
Christine, yeah.
Ah, it's nice. I didn't know.
Yeah. Probably so next time you can come with them and visit us our institute for some days and some weeks. And you probably also have some connection with Beijing Institute, some LOAC people there.
Yes, yeah. I mean,
Okay. Yeah. Probably you can also go to Beijing. Yeah.
Oh,
Okay.
thank you.
Yeah. We can talk about later.
Let me come around. Right. Thanks for being here.
Yeah, I would like to we have a postal there, but continuum and cosmological science interest plus room science. Science also, yeah.
Please put your